Oh, you're live. That's great. Okay. Nice. Wait, what is the link to this? Oh, copy video URL. Okay. Wait, if you are here... Oh yeah, okay, I'm gonna announce. I'm gonna start, I think, soon. Can people hear me? Wow, hello, okay. Starting. Okay. OMG. Hello, it's Yume. Hello, everyone. Okay. We are starting. By the way, can someone check just the YouTube video if they can hear me? Wait, actually, maybe I should, I'm thinking. Should I share my screen on Discord as well? Maybe I should. Oh, that's crazy. Wait, this should be working, right? Yeah, okay. I think this is working. Okay. Right. Well, welcome everyone. We haven't, I don't know if we've had a live solve. I think the last live solve was like Yume's 13-hour informal live solve, right? When was it before that? Okay. Well, I guess we can get started. What is the time? The time is, for me, well, I'm just gonna put the UK time. It's currently 13:09. That is when we are going to start. Alright. Here is the paper. I have not looked at this. I need to screenshot some stuff. Alright, so first I'm going to paste it here. And then for those people on the stream, I think what I need to do and save as. Okay, that's problem one. Does this work? Image. Image file. Okay, wait, this should work. Oh my god, it works. Okay. And I should put this up here. Yo, this is so legit. Okay. Okay, let's start solving. Is it the keyframes are not being sent off and around, which can cause buffering? Oh, interesting. Maybe I'm trying to do too much. Okay. Is it oh, audio is working. Okay, I checked it. Okay, great. Okay, let's actually start now. Okay. For any two positive integers m and n, we define lmn as their least common multiple and hmn as their highest common factor. Okay, yeah. Given a prime this, let k denote the number of ordered pairs of positive integers satisfying this equation. Okay. Determine the smallest possible value of k across all choices of the prime p greater than 3. Okay, wait, this seems extremely... Okay. Alright, well, let's try some small cases, right? So, let's pick p equals 5, right? What do we get here? We get 625. And we need to find the number of...
Yo, what's on me?
M and N. Yo, it's Yume. Hello.
Yo, your Discord screen share is not working.
My Discord screen share is not working. Okay. I guess it's not working then. But the that is no one problem. I guess people can watch. Actually, no, wait. Let me just share. Yeah. Wait, let me share the thing so people can view. There we go. Okay. Enable shareable link. Oh, right. People can view that. Copy link. Okay, well, I'm going to stop screen sharing because I don't think it works. Right? This is a known problem with my...
Wait, can I also do Livesolves whenever I want?
I mean... If you... I mean, like, you can, like, check with me and then... Well, I just check with the mods, right? But yeah. You kind of already did, didn't you? Like... Okay, you can follow the whiteboard here.
No, that was on the lounge VC, not the Livesolve thing.
Yeah, well, I mean, you can do it in Livesolve as well. I mean, if you're, there are like 3 main things, right? Firstly is like, you need a good enough mic. The second one is, you probably want to have something to write on, otherwise your writing will not be very legible. And the third one is like, are you good enough? And if all of those are satisfied, then yeah, you can Livesolve. I mean, this is not just for you, right? It's like for people in general, right? If people want to Livesolve, because like technically, like anyone can just apply to be a Livesolver. This used to be a thing back in the day, but it's like hasn't like been run for.
Can I do like slop Livesolves with like good enough mic?
Sorry.
The slop Livesolve.
What's a slop Livesolve?
Like, it's not gonna be on YouTube and stuff.
All right, no, it doesn't have to be on YouTube. Like, if you don't want it to be on YouTube, then like,
It's like if I'm like grinding out math or something, then I can just like Livesolve it if I have a good enough mic.
oh, I mean, like, just grinding, then probably no, right? I mean, like, that's not. Yeah, like it has to. It should be a contest in theory. Like that's what we've always done, like in the past.
Oh, okay.
Yeah, and it should be like. I mean, yeah, it should also be like a. Like usually what happens in the past is like before you came, right? Uh, a contest would happen, and then like people from like Helper Lounge or something would be like, "Yo, who wants to live solve this?" And then like I don't know, we'd get like 1 or 2 people, and then we'd schedule a time to live solve, and then it'll be a thing, right? And then we'd like stream it to YouTube. It hasn't happened for a while, but yeah, that's generally how it used to happen. Anyway, we can talk more about this. You're eating into my time.
Well, I gotta sleep now, so
Okay,
bye.
all right, see ya. Bye
Bye bye.
all right. Anyway. Okay. Let K denote the number of ordered pairs of positive integers satisfying this equation. Okay, LCM plus. What? Oh my god! Is it? Why are they using L and H? Honestly, can they not just use LCM and GCD? That's what it is, right? It's the least common multiple, and H is the highest common factor. That's just GCD. Yeah. Okay. Well, I'm gonna just LCM and GCD this, honestly. Okay. Yeah. So we've got this thing. This seems extremely sus to me because if you look at the factorizations of M and N, you know, one of them is going to be like the minimum of all the exponents, and the one is going to be the maximum of all the exponents. And surely, like, if you just VP bash, I don't know, like, right? Yeah, because like, if you plug in some numbers for M and N, you've got like, can you even get this to work? Because right now, all I see is like, oh, you can get like 1 and like 624, right? And so the LCM is going to be 624. And the GCD is going to be 1. Okay, so if you add them together, yeah, sure, you get 625. And because it's ordered, you're going to have 624, 1, and 1624. All right. Okay. Do any other pairs even work? I'm guessing it does, because otherwise it's going to be kind of trivial, isn't it? I mean, what? You're supposed to get the smallest possible value of K. So I'm guessing that like this P is actually kind of like not trivial to find. Like it's not 5, I'm guessing. Okay, well I'm guessing you can do something like 620 plus 5 equals 625, right? Because like if you just use these two numbers, then one is divisible by the other. So then, right. Interesting. Wait, but isn't this true for like all of them? Like you can just do like p to the 4 minus 1 and 1, right? And like 1 and p to the 4 minus 1. And you can also do like p to the 4 minus p with p, and the flipped version of that one as well. And then, you know, you can keep going, I think. Minus p squared with p squared, and, you know, the flipped version of that. Minus p cubed with p cubed. Wait, once you get to this point... Oh, no, it's still fine, yeah, okay. Yeah, I think this still works, right? Because, like, the LCM is just going to be the bigger one, and the GCD is just going to be the smaller one. So they still add up to that. Okay, so the minimum value for K, I think, is 8 for any choice of P. I think we've established that. And I think it helps that P is greater than 3, because then it's actually possible, right? Okay. What do we do now? So I think in the case of 5, let's see if like there are any other pairs that work. So, but if this seems what? Okay. The thing is, right? If there are two numbers that did work, if they share some factor which is not 5, then it doesn't work anymore. Surely. Yeah, because then that means... Yeah, okay, so that means that P has to divide in and... Sorry, if some prime divides M and N, it has to be 5. Right, so it's like, let's say 7 divides M and N. then the GCD and the LCM will both be divisible by 7. And so p to the 4 supposedly divisible by 7, which we obviously know is not true. Okay, so in other words, what we've just shown here is that if p divides both m and n, all right? Oh, let's say q. Okay, if some prime q divides both m and n, then q equals p. Okay, and what about if m and n don't share some, like, I don't know, if like m is divisible by 2 and like n is divisible by 3 or something, right? So let's say, I don't know, like m equals 5 to the a, 2 to the a times 5 to the c, and n is like 3 to the b and 5 to the c, right? Then the LCM is going to be 2 to the a, 3 to the b, 5 to the c, and the GCD. Oh wait, the multiples, the powers of 5 can be different. So okay, let me take that into account. This is going to be 5 to the d now. Okay, so the LCM is going to be it doesn't matter. We'll just do it like max CD, right? Here. And the GCD is going to be, like 5 to the min CD? Okay, so you add these together, and you need to get 5 to the power of 4, which is extremely sus. In fact, I think this proves that C has to equal D, because if it doesn't, you factor out min CD, and you get like 5 times the min. Okay, I'm just going to say this equals little m and this equals big M, right? 5 to the min times 5 to the... Wait, what? Yeah. Max minus min, 2 to the a, 3 to the b. And this part needs to be a power of 5. So we've got a power of 5 here, and obviously this part cannot be a power of 5. So that would mean that a equals... A and B both are 0, right? And in fact, I mean, this doesn't just work for like 2 and 3, obviously. Like, it works for anything else, right? Any other prime factors of m and n, right? That is, if they divide different powers of 5. So if they're divisible by different powers of 5, then they literally cannot be... They cannot have any other factors. Wait, what? Am I tripping? Wait, what? Oh, I'm not tripping. Yeah. Okay, so if they divide different powers of 5, then everything else has to be 1. Okay, but if they divide the same power of 5, then you can get these 8 examples where you do have other factors. Yes, okay. Okay, so here we've proven that if C is not equal to D, then M equals 5 to the C and N equals 5 to the D. Right, so it can't have any other factors, because this part needs to be a power of 5, which it isn't. That's very sus. Okay, and meanwhile, if C does equal D, okay, this means you now have like m equals, let's just say m equals 2 to the a, 5 to the c, and n equals 3 to the b, 5 to the c. Okay. Now once again, the GCD, wait, maybe we should do LCM first. LCM is 2 to the a, 3 to the b, 5 to the c, and the GCD is of course 5 to the c, and then you can like, you can add them up. So the sum is going to be 5 to the c, 1 plus 2 to the a, 3 to the b. And once again, this has to be a power of 5. And once again, this is not like, 2 to the a, 3 to the b. It could be any other factors too. Okay. So I think this is fine, right? Like, all you really need here is like C can be like 0, 1, 2, 3, 4. And so this part can be 5 to the power of 0, 1, 2, 3, 4. So I think, there are now like 4 possibilities, because okay, this can't be 5 to the power of oh no. It can't be. It can't be 5 to the power of 0. So it can only be 5 to the power of 1, 2, 3, 4. So there's like 4 possibilities. And then the problem is now, like, obviously, you need to figure out how many different factorizations you can have, right, in order to get to those powers of 5s. Okay. So essentially what this means is that you generate like some other pairs that work for p equals 5. Yeah, I mean, I think at this point I've pretty much solved this problem. The rest is pretty much just busy work. Because, okay, yeah. Like, we can break down into cases, right? If this is 5 to the 1 times 1 plus, if this is 5... no, this could be 5 to the 0. Right. And this could be 1 plus 5 to the 4 minus 1. Okay, and then it's just a matter of, like, how many ways are there to, like... What is the factorization of 624? Wait, let me just write this in directly. This does work, right? Okay, anyway. Factorization of 624, that is... Wait, let me do this in a different color. Okay, so we've got a 2 and a 3, 12, and a 2 and a 1, 5, 6, and a 2 and a 78. Well, I haven't got this wrong, right? 2 and a 39, and that's a 3 and a 13. Have I got those right? That's 16 times 39. Okay, let me check this. Okay, that's 54. That's 14. Okay, and that's 40. 480. You get 4, 2, 6. Yes. Okay, that's the correct factorization. Okay. So at this point, you see that 624 is equal to 2 to the 4 times 3 to the 1 times 13 to the 1, and you're like, okay, that means that, depending on the number of factors this number has, the number of different prime factors is the number of different ways to like generate the pairs. So okay, using this we can generate some more pairs. For example, m could be 2 to the 4, and n could be 3 to the 1 and 13 to the 1. Right? So I think this works, and the reason it works is because, clearly the LCM is going to be 624, and the GCD is going to be 1, right? Okay. So then there are like lots of different ways you can generate this. In fact, there are going to be how many? 8, right? Because you just essentially choose a subset of the primes that divide it. There are 8 such subsets. Pretty happy with that. So there are 8 solutions in this case, right? Okay. Then you've got the case where like you've got 5 to the 1 going on. So you've got the you want the GCD to be like 620. Sorry, the GCD to be 5 and the LCM to be 620. Okay, so then what's the factorization of 620? It's 5 times... it's just 2, 5... there's 2 squared times 5 times 31. If I'm not wrong, this should give you another 8 solutions. But I should check this one. Hang on. Right, because it's just 10 times 62, yeah, and 31 is prime. Okay, so we're good. So it's this one. I need to write better. Okay, and what do we have here? This generates stuff like m equals 5 times 2 squared. Oh, wait, there's a 5 here and a 5. Oh, wait, does that matter? Let's see. Let's say we put the 5 in here. And then n can be like, 5 times 31. Okay. So the LCM is clearly 5. Sorry, I mean, the GCD is clear. Oh my god, guys, like, please. Okay, it's late over here. Okay, not that I'm sleep deprived at all, but I'm just using it's late as an excuse. So the GCD is 5, and the LCM is gonna be 5 squared, 2 squared, 31. Yeah, no, that's right. Because that's 620. Wait, what? Is it 620? Hang on a minute. Oh my god, guys, I'm high. There's no 5 here. What am I talking about? It's literally just 2 squared times 31, yeah? Okay. Yeah. It's late, guys. It's late. That's why. Okay. Okay. So we can do this. Right. And then the LCM is, of course, going to be 5 times 2 squared times 31. And the GCD is, of course, going to be 5. And this guy here is 620. And this guy here is 5. So we're good. Okay, so if I'm not wrong, this should generate 4 solutions because you've got 2 different prime divisors of 620. That is not 5. Right? You don't include 5. Okay, you work your way down once more. You do 600 for the next one. Now 600 is, just 5 squared times 2 squared times 3. That should be it, right? No, it's 2 cubed times 3. Because it's 10 times 10 times 6, yeah? Okay. Let me just do a sanity check, right? So both of them have to divide 5 squared, right? We've established that. And I think this means that, you could have like a 2 cubed here and a 3 to the 1 here. And then the LCM is going to be 2 cubed, 3 to the 1, 5 squared. And the GCD is, of course, just going to be 5 squared. And this should be 600. And this should be 25. Okay, so you should have 4 solutions here as well. And the next one is the last one, not sure. But you should have 500 times 500 and 125, right? So this would have 5 cubed in it. And you just multiply by 2 squared. Okay, so this one only has 2 solutions. And then what would the next one be? It would be, it would be like 0, right? Okay, and obviously that's not. Is it positive integers? Yeah, positive integers. Okay, so that means you can't have like 625 and 0, for example. Okay, so we found 8 plus 4 plus 4 plus 2. That's 18 solutions of this format in total. When p equals 5. Okay, so that's in the case where c equals d. Now what if c does not equal d? Now I'm pretty sure in this one, it's just some of these solutions that we've gotten here, right? Oh no, wait. Oh yeah, okay. Oh yeah, okay. So if c does not equal to d, there are no solutions because if m is 5 to the c and n is 5 to the d, that means let me do LCM. The LCM is 5 to the max, right? And the GCD is 5 to the min. And you do like 5 to the max plus 5 to the min, that's not going to give you 5 to the 4. Because they're 2 different powers of 5, right? You like factor out one of them, and then the other one you get like 1 plus 5 to the some power, and that does not have a 5 in it. Okay, so C has to equal D actually, so this case doesn't even work. Okay, you can like ignore this case. That means I think there are just 18 solutions, right? Okay. So I think you kind of just repeat this with some other primes, and like for some reason, yeah, maybe we're not completely done, right? But you know, I think we're pretty close. So the reason, okay, so the quick way to get 18 solutions when p equals 5. How can you do it? So you get, when p equals 5, you get 624 being equal to, or actually I should just say like, there's 4 to the 4, okay. 5 to the 4 minus 1 is equal to 2 to the 4, 3 to the 1, 13 to the 1. And because there are 3 factors, 3 different prime factors, right? You take 8 solutions. That's 2 cubed. Okay, next you've got 5 to the 4 minus 5. And of course this one, we also figured out that's 5 times 2 squared times 31 to the 1. So 2 squared, we can ignore the 5s, but we'll write it in anyway. 5 times 2 squared times 31. Right, and since it's got 2 different prime factors, you've got 4 solutions. And then we've got 5 to the 4 minus 5 squared, and same with 5 to the 4 minus 5 cubed. Right, this one is just 5 cubed times 2 squared. So you've got 2 solutions here. This one is 5 squared times, which one is it? 2 cubed 3 to the 1. Okay, so this one also gives you 4 solutions. So I think you just kind of like repeat this over each prime, and that should give you the number of solutions for each prime. Okay, and for some reason, one of them gives you like a lower number and you can prove it, I guess. So let's try p equals 7, another small case, right? Do I really want to do this? Because I'm guessing you just prove that like, oh, one of them, you know, will always have like 4 different prime factors, and then it'll give you 16 immediately, and then the other ones will give you at least 1, 1, 1 each, and then you just like finish, right? Surely this all happens. Okay, let's test it, right? Like we've got 7 to the 4 minus 1. 7 to the 4 minus 7. 7 to the 4 minus 7 squared. And 7 to the 4 minus 7 cubed. Okay. Is it true that one of these... I don't know how to factorize these. Oh, wait. No, wait. What am I talking about? Wait, this is... all of these are like what? Like not too bad to factorize, right? I mean, this one's just... Let me just do this in general, actually. Why am I doing this for small cases? P equals P. Oh my god, look at that, guys. A genius. Okay. P to the 4 minus 1, that is, of course, that's p squared plus 1, right? And let's go p plus 1 and p minus 1. Okay, so just like that, we have 3 4? Is that 3 or 4? Isn't that 4? 4 different prime factors? Because one of them is, well, they all have a 2 in them, right? And then after you divide out the 2's, oh no, wait, oh my lord. Wait, I feel like this problem 1 is like, am I just like, I mean, like, you know, I think I'm like pretty close to the end, but like this problem 1 feels like it. I mean, it was harder than expected, but maybe it's because I'm live solving, and like, I don't know, your brain is on like 60% capacity when you're like live solving, right? But anyway, like, cause okay, these 3 are all coprime, right? By Euclidean algorithm, they must be coprime, right? These 2 are, of course, sorry, I mean, they're coprime once you like remove all the 2's. Okay. Cause yeah, like these share, the GCD is 2, yeah. The GCD of these should also be 2 because this is a factor of p squared minus 1, and so is this one. Yeah, okay, yeah. So pairwise, you know, GCD is at most 2, which means that you've got at least 3 factors. But the only way you have exactly 3 factors is if one of them is a power of 2. And the other ones, when you take away all the 2's, you get left with a prime, which I think is quite rare, right? Okay, I mean, when p equals 7, then this one is 8. So you literally get 2 cubed, and then you get like, here you get 6, which comes into like 2 times 3, and then here you get 50, which is 2 times 5 squared. Okay, so based off these, okay, you get 3 factors. Okay, so this gives you 8 solutions. Let's do the other ones as well, right? Okay, maybe we have to do the other ones. Okay, so p cubed. Oops, no, p to the 4 minus p. P to the 4 minus p. So you've got a p straight up. Oh, but the p we're not considering the p, right? Yeah, the p is like built in. Okay, so then you've got p cubed minus 1. Now the p cubed minus 1 can be factored into p minus 1 and p squared plus p plus 1. Wait, is this the right factorization? Yeah, it is. Okay. What does this tell us? These two are surely the GCD is at most. The GCD is 2, right? Because this one you've got p squared minus 1, and if you add itself, oh wait, what? I don't like this. You add itself, you get p squared plus p minus 2, which differs with this for 3. Okay, but 3 is a prime, so we're fine, surely. Oh, no. This is how you prove that, like, the minimum is 18, right? Okay, so this one gives you, we know this one gives you 8 solutions. Bro, this is gonna be so messy to write up. I'm not looking forward to this write up, but fortunately I don't think I have to write up anything, so that's fine. So we know this one gives you at least 8 solutions because it gives you 3 distinct prime factors, right? This one gives you at least 4 solutions because, like, you know, all of these are greater than 3, and we know that the GCD is 3. Okay, so I can like, you know, put this in brackets. You know, you've got the pairwise GCD. Pairwise GCD is 2. Here you've got your GCD is 3. So you have at least 2 prime factors. So you've got 4 solves in this case. Okay. Now with your p to the 4 minus p squared. Whoops. Okay, with your p to the 4 minus p squared, you've got your p squared times p minus 1 and p plus 1. Of course, this clearly the GCD here is 2. I should fix this. The GCD is less than or equal to 3, right? It's either 1 or 3. Okay. GCD being 2 means that you're also going to have at least 2 different factors here, so that gives you 4 solves. And then when you have p to the 4 minus p cubed, that's going to give you p cubed times, should I take back what I said? Maybe the write-up isn't going to be so bad. P cubed times p minus 1, and of course this is going to give you at least 2 solves, because p minus 1 is obviously not 1. And it's not p, right? Oh yeah, wait, we also need to show that like all of these are co-prime with p, which they obviously are. Okay, well, we'll just make a new note about these, right? Like, these things are all co-prime with p. That is also important. All co-prime with p, which you can prove easily by Euclidean algorithm again. So once again, you just add these up and you get at least 18 solutions. And when p is equal to 5, you do get 18 solutions, thereby proving that you can get 18, and therefore that 18 is indeed the minimum possible value of k. 18 is the minimum. And it is achieved. What the? That's not how you spell achieved. Wait a minute, what the heck? No, it is how you spell achieved. No, wait, I'm searching this up, sorry guys. Yes, that is how you spell achieved, okay. Achieved by p equals 5, right. Okay, cool. We're cooking. Let me check the chat. Alright, seems decent. There are like 3 different chats I have to check. Okay. Seems pretty good. Okay, nice. Everything seems to be going just fine. Alright, next problem. Also, oh, it's the geometry problem. Okay, that's good. That means I'm not going to struggle with the geometry problem for a super long time, because my geometry is like half as good as my combi. And when I say that, I mean that in the sense of like, my geometry is probably like D7, and my combi is like D14. Okay, maybe it's not actually D14, but it's like, it's close. It's greater than D10. Let's put it that way. Okay. So hopefully I can solve this geometry in like not too long. Okay. Let me paste it here. And also I need to configure the stream a little bit. Bear with me, guys. Oh wait, I need to save it first, don't I? Yeah, now it should work. Oh, I see how this works. I remember how this works. Okay, there we go. Alright, let's do this. This problem should be maybe like D4, D5-ish. But I feel like the first problem was kind of D4, so I don't know. Maybe it was just harder than normal P1. The convex quadrilateral ABCD has sides AD and BC not parallel. Sure. Let me draw a mini diagram on the side first, just to get a feel for it. Disclaimer, guys: when you actually do geometry, please draw like a. Please draw a good. I will be drawing a good diagram in a minute. Okay. A D A B C D. The diagonals AC and BD intersect at X. You know, we cooking. I mean, it looks like an X, right? Wow, look at that! I'm a genius. That's why they called it an X. The perpendicular bisectors of sides AD and BC meet at Y. Huh. Alright. That looks pretty good. Okay. I think that's roughly where Y is. Suppose that Y lies strictly inside triangle XC. Close enough. Prove that AC equals BD if and only if XY bisects DXC. What the heck is this condition? Only if, okay, XY bisects DXC. Huh. Okay. Okay, let's draw an accurate diagram first, right? So yeah, okay. Let's draw AD. Let's draw AC and BD like, you know, equal first, and then we can figure out how to get the rest of this. Wait, I need the other rubber. Oh, yeah, let me just draw this first. Okay. We need the pixel eraser now. Okay, let me try and get this right. Does this look right? I mean, when AC equals BD... Wait, what? Yeah, okay, maybe I should make it not look so much like a parallelogram by extending this side. Okay. That looks roughly right. I have a feeling that the only if part is a lot easier to improve. So I think I'm just gonna start with that. Okay, I think y lies inside dxc. Actually, you know what? Like, I think the main thing is like you just intersect two of these, and then you just like whatever triangle it lies inside, you just call that dxc, right? Like, surely that's the meta here. Okay, so you've got A, B, C, D. Anyway, I think it works in our case. Anyway, I'm gonna use a different color. That looks pretty good, actually. Okay, that's y. Okay. I guess my first question is like, are there no cyclic quads in this diagram? Oh no, there's two right angles. What am I talking about? I don't know if the two right angles help that much though. I mean, like the cyclic quad, right? You could get a cyclic quad like by like just intersecting these two, which for the sake of this diagram, I'm gonna say they like intersect here. Okay. That's so bad. I'm gonna. There we go. So they intersect here. Hey, wait, you know what we can do? Oh my god, wait. There's this genius thing that you can do when you're on a whiteboard. It's called moving the whole thing. Am I cheating, guys? Is this cheating, chat? Oh my god, I'm such a genius. Okay, that's roughly correct, I think. So like there is a cyclic. I don't know. I really do not have that much faith in. Oh, actually. Wait. Nah, surely not. Surely not. Wait. What the heck is this doing? Does this pass through X? Let's call this point P, yeah? Why would it pass through X? Okay, wait. Oh, wait, it's the perpendicular bisector of AD and BC. This is some kind of, like, weird, like, it's almost the circumcircle construction, but it's in a quad. I wonder if there's, like, we can do something with that somehow. I'm not convinced though. I think it's a bit sus. Wait, we should call these things names. Oh my god, we should name them. Alright, let's call this one M, and this one is going to be N, right? Okay. See, the thing is, like, if PXY are not collinear, because if they are collinear, right, then things just work. Like, this is also an angle bisector. This is an angle bisector. Wait, is that intentional? I mean, see, okay, like, if PXY are collinear, that feels right for a problem of this difficulty. But, like if they're not collinear, I like, genuinely I don't know what to do, right? Because, like, otherwise, I mean, I feel like you could, like, chord bash this. Oh, no, but this, actually, you probably could chord bash it, but, like, I'm not going to. Yeah, Cause like, yeah, wait, what? Yeah, no. Well, I mean, these two are not the same, right? Because that would mean, like, if these two are the same, like if my and ny are the same, then these two are the same. Because then we have. Wait, no, wait, what the heck? What? No, I'm high, guys. Wait, what the heck? Yeah, no, yeah. Because then also these two are the same, right? Yeah. Well, I mean, at the very least, if you draw this in with py as the diameter, it would pass through m and n. Okay, a circle with py as the diameter passes through m and n. This is the point where if I had a really accurate diagram, it could really help. But unfortunately, this diagram is not accurate enough. Okay, I mean, if it's not, right, let's say px and y are not collinear. Right? How are you supposed to prove this problem? Surely, like in some sense, I do feel like, actually, maybe there's like another way to do this, right? Yeah, because, wait, okay, like if you, okay, wait, different color, sorry, okay, YB, YC, okay, these two triangles are the same, and these two triangles are also the same. Fascinating. Oh wait, oh my lord. Wait, I forgot that AC equals BD. What am I doing? Oh my god. Literally, it was not even using a condition. Okay, wait, so what can we do with AC equals BD? Okay. It feels like you can trig bash this too, guys. AC equals BD. Okay, imagine like, I don't know, like let's say we take this line BD here, right? And like let's say we try to like move it around somehow. Apparently, so clearly the line NY does not change, right? Like obviously the point Y changes if we move BD around. Oh no, wait, N and M both change. Hang on, what the heck? Yeah, like no, wait, everything changes. Oh, that's crazy. Oh man. Okay, wait. Because AC is supposed to be equal to BD, I no longer think you can chord bash this. But I do think maybe you can trig bash it. But I'm not going to once again. Interesting. So, imagine moving B and D along this line here, right? So like, you take the line BD, you move B to the left, and you move D to the left at the same rate. Well, like, you move them by the same amount, right? X stays the same. And so does the angle DXC, which means that the resulting Y should stay on the same line. So in other words, if you move B this way and you move D this way, Y should move on this line. Why is that true? Bro, I'm using MMP, guys. I'm using method of moving points, guys. Wait. yeah, I really doubt MMP works here. I mean, I can't see a way to make it work, unfortunately, but what I can see, maybe, yeah, okay, wait, maybe I should remove these lines. Okay. Let's try a more traditional approach, guys. Okay, maybe that was overkill. All right. So what can we do here? The thing is, like, there are no. Well, I mean, unless this PMYN thing is a cyclic quad, like there are no cyclic quads here. The fact that it's a convex quadrilateral makes it very hard to angle chase stuff, right? And yet you're supposed to prove somehow that this is an angle bisector here. That is quite interesting. What is the property of y? Like, is there some other characterization of y that we can use somehow? So we know that like ya equals yd, right? And we know that yb equals yc. Okay, well, I mean, it's the only point that does that. Okay, well, obviously, these two are isosceles triangles, right? But what if you look at, like, I don't know, these two triangles? They have the same two sides. Okay, wait, guys, wait, hear me. Wait, what the heck is going on? Wait, what the... Wait, is this angle the same as this angle? Oh, yo, chat, wait a minute. Wait a minute, guys. Oh, yo. Okay, I figured out how to use the BD equals AC condition. So, okay, so you've got your triangle here. You've got your AYC triangle, right? Look at this. The AYC triangle, right? It's got one black length, right, AC. It's got one blue length with one dash through it, and it's got one blue length with two dashes through it, right? Okay. Right. We've got the triangle. We've got the triangle. Wait. Triangle. BYD. Yo. Isn't that a Chinese car company? Okay. That is exactly what I'm talking about. That's BYD, guys. BYD cars. Right? Well, I'm Chinese, so it makes sense. Right? I am inserting Chinese propaganda. BYD also has one of these black lines, right? As BD, we know that's equal to AC. We've got YD equals YA, and we've got YB equals YC, guys, which means that these two triangles are, well, okay, well, maybe you should write it like this, right? BYD. Okay, they're congruent. Trust, chat. They're congruent. And because they're congruent, there is, guys, look at it, check this out, right? The rotation at the point Y, taking D to A, it also takes B to C. So it takes the line DB to AC. I mean, this is all kind of trivial, right? If you maybe I should actually rub out some more lines, okay, to make this clearer. Right, you do like this, okay? Yeah. This is good. Okay. You take this triangle, rotate it at Y until it becomes AYC, and I'm pretty sure that just does it. Like, surely that just does it, right? Why does that do it? Because this angle is equal to this angle, right? Okay, wait. Yeah. So you've wait. What? You've rotated D to A by an angle of say like theta. Okay. Let's call this theta. Wait, let me use another color. So this red angle here. Whoa. Wait, what? What? Are you kidding me? Are you saying this is a cyclic quad? Have I missed this the whole time? Bro, guys, I legit thought that was not a cyclic quad, bro. Did I get baited? Because, okay, the rotation that takes D to A also takes DB to AC. Okay, so you've essentially just rotated the line by the same angle, which means that this angle should be... Wait, what the heck? I thought it was equal to this angle, but it's not, right? It's equal to this angle. Anyway, I don't think any of this matters, because the fact is, wait, why am I... Okay, wait. You literally don't even need this, right? Because, like, take the height from Y to BD. It's going to be really hard to draw, guys. Take the height from Y to AC. These two are the same height, but they're both perpendicular. Okay? They're both perpendicular. And that's enough to prove that xy bisects angle DXC. Because you've got the, you know... You've got the angle bisector construction, right? Right angle, triangle. Right, this guy equals this guy because we know they're the same triangle. And this guy equals this guy. Okay, so therefore, it's an angle bisector. Okay, we're done. Okay, so we've done the only if part. And I think the reverse should not be too hard now. So in other words, okay, let foot perp. Actually, wait, what am I doing? Let P be on BD such that YP is perpendicular to BD. So this point is P, and this point is going to be Q, of course. Q is going to be part of AC such that YQ is perpendicular to AC. Okay. Okay, so now we just have, of course, that YQ equals YP. And of course, XY equals XY. And of course, the angle YQX equals the angle YPX equals 90 degrees. All right. And yeah, that's enough to show that the angle YXP equals the angle YXQ. So we're done in this case. Right. So now we're going to start with XY bisecting DXC. And we're going to show that AC equals BD. Is one harder or easier? I think it's... I feel like it could be harder, actually, this one. All right. Well, let's do it. Okay, so we've got same diagram. In fact, one cool thing about doing this is that, like, look, guys, if I had a ruler and compass in this app, I would be using them, but I don't. So I'm just gonna be copy pasting this diagram, right? In fact, I can even zoom in on this now. Wait. Oh, there we go. Okay. And I can also erase some more stuff. Erase this. Erase these. P and Q don't exist anymore, of course. No, wait, no, they can exist. Oh, I don't know if they're useful though. Oh no, surely they're useful. Surely they're useful. Because what do we have to prove? We have to prove AC equals BD, right? Wait. Isn't this literally just like the same argument but like the other way around? Because what? What do we have? YQ equals YP. We know that. Okay. Wait, let me just make it clear here, right? This here up here I'm proving that AC equals BD implies XY bisects. Okay. Down here I'm proving that XY bisects implies AC equals BD. But surely what you do here is you construct P and Q in the same way. Now we know that YP equals YQ because XY is an angle bisector, right? Because Q equals angle bisector. Right? And surely this just shows that like triangle YPD is congruent to triangle YQA. Why is this? YQA, YPD. Okay, because yeah, they have right angle, the red line, and they also have the blue line in common, right? And we also have, of course, that where is this? YPD is YQA, yep, and we have YPB is congruent to triangle YQC. Same reason. So these both, yeah. RH. Right triangle. Wait, why is the abbreviation RH? I never figured out actually, but it's RH, I guess. Right triangle. Huh. And so, of course, right, we get that PD equals QA and PB equals QC. You add these together, you get BD equals AC. Okay, now we're done. Okay, that should finish up the geometry problem. Let's move on. Let's check the chats. Guys. Yo, let's go. Someone asked, are you in Melbourne right now, Tony? The answer is yes. Alright. Doesn't GeoGebra exist in BMO universe? That's a great question, you know? I feel like using GeoGebra is cheating even if I used it to construct a diagram, because the thing about that is it's too easy to just say like oh, this diagram doesn't look right, let me just move this point over here, right? Whereas in real life you would have to like reconstruct the whole diagram if you want a point to be moved. So I do feel like using GeoGebra is so I try not to use GeoGebra like in Livesolves. That's why anyway that solves problem 2. Not too bad, right? We haven't done the combi problem yet. That should be a breeze when I get to it. I'm a combi main, guys, in case you don't know. Oh my god, it's the combi main. That's crazy. Oh my lord, it's this problem. I remember this problem. So this problem came up in the mods chat because people realized that this problem is like not original at all. In fact, I think it's part of some like old IMO SL. What was it, IMO SL? Something like some like obscure. No, it wasn't that obscure. I remember it was not obscure. It was like some previous source had like a very, very similar problem. It could actually be exactly the same. Oh no, it's this one is slightly different. I just realized now. But yeah, I haven't thought about that problem, and obviously I haven't seen this problem, so it should be pretty much still a live solve. Each number appearing exactly 300 times. Okay, is it possible that the 60 row and column sums are all different? Right. fascinating. Let me configure some stuff. Let me paste it in here first. Okay, we have to pay problem 3, and gotta go configure the stream as well. Let me now add an image, P3. Browse P3. There we go. Okay, now P2 is gonna disappear. And move P3 over to here. Cool. That's gonna be it. Alright, let's try this. Wait, oh, that means problem 4 is gonna be algebra. Wait, let me have a look at problem 4. Okay, doesn't look too bad. Doesn't look too bad. It looks like a it looks like an algebra I can solve. Right, let's put it that way. Because there are some very technical algebras and there are some very visual and intuitive algebras. And this looks like the visual kind, but I might be wrong, obviously. I haven't really looked at it. Anyway, let's do this copy first. So, each cell of a 30 by 30 grid contains one of the numbers -1, 0, or 1, with each of these 3 numbers appearing exactly 300 times, because there's obviously 900 numbers in the whole thing. Is it possible that the 60 row and column sums are all different? Right. So, okay, so, alright, some kind of like preliminary observations. Firstly, you can rearrange all the rows and columns without changing the properties of this, so you can probably log some stuff, right? Secondly, you can add or multiply anything, like, you know, -1, 0, and 1. You can apply any linear map to these. In particular, you can use like 0, 1, and 2, I think, right? Like that shouldn't change stuff. And in fact, if you use 0, 1, and 2, then like all the sums are just, you know, you've got 0 up to 60, right? So, okay. Do I think it's going to be better to use -1, 0, and 1 or 0, 1, and 2? I think for symmetry reasons, I think using -1, 0, and 1 is probably better. I think that's the best justification I have right now. So I'm going to stick with -1, 0, and 1. Yeah. And I also think it makes it easier to like draw things without having to like write it -1s. You can just draw like I don't know. You can draw like an X or something, you know, and a tick for 1, right? Anyway, I think it's just better. Yeah. Let's try a small case, by the way, because this is definitely very big. Let's do like a what? I don't know. Does it matter that it's divisible by 3? Let's do like a 6 by 6, I guess. I really don't think it matters that it's divisible by 5, right? That's why. Okay, so let's do a 6 by 6. Now, of course, the row and column sums can only be of the set -6 up to 6, and by pigeonhole principle. Well, it's not by pigeonhole principle, but like if you take 12, there are only 13 numbers in here, so you've got 12 different numbers, so one of them is going to be left behind, right? Which is already a very strict. Okay. Yeah, that does seem like a very strict thing. Now, each number in this one is going to be 12 times, okay, and here's the thing, right? Like if you just do a whole column of 1s, okay, then you can get 6. Oh, right. Okay, then if you want -6, I mean, you obviously can't have a you can't have a row that now goes to -6. In fact, the maximum row sum possible is now 4, right? I mean, minus 4 is the minimum row sum possible. Okay. So if you want to get -6 or -5, you have to use a column to do it. What's the other thing? There's a parity thing, right? Like a double counting argument here. I don't know if that helps much, but I think it says that like the total sums of these. Oh, firstly, wait. The sums of these and these are the same. Oh, wait, and because each number appears the same number of times, the total sum of these and these must be 0. Wait a minute. Wait, that's sus. Yeah, because like the column sums, if you add up the column sums, it's just the sum of all the numbers in the grid. And if you add up the row sums, it's the sum of all the numbers in the grid. So they both have to be 0. Wait, can you even get like... I mean, you definitely can, right? You could have like, 6, oops, 6, 5, 4, like -4, -5, -6, and then you have like, 3, 2, 3, 2, 1, -1, -2, -3, like, right, that's possible. Okay. But now, notice that in order to have 6, 5, or 4 at all, that's too many ones already. Like this 5 can only be made with 5 ones and a 0. And this 4 can be made with 4 ones and a 0 or 5 ones and a -1. Like the only 2 ways to make that. But even if you've got 4 ones and 2 zeros, that's already like way too many ones. I feel like this is very restrictive. Because in this case, yeah, you've already got 15 ones, which is way too many. So you okay, well, I mean, all that says is like, oh, you can't have like all the big numbers as the rows and But I wonder, like, in the 30 by 30 grid, like, do you even need... let's pretend now this is a 30 by 30 grid. And obviously, you can't have all the numbers from like 6... Wait, what, no? Yeah, wait. Oh no, okay. So now the possibilities go from 30 to -30, right? Okay. And obviously you can't have like 30 and 29 and 28 and all the way like down to 15 and then like -15 up to like -30 or down to -30, I should say. Because that would need too many ones, right? Because you need at least this many ones. Yeah. That's a given. Like to make a 15, you need at least 15 ones. Okay, yes, because even if the rest are zeros, you still have 15 ones. But this means yeah, okay, maybe this argument doesn't disprove it, because like, okay, well, the sum of this is not that large, right? Like, what is it? You've got 15... wait, what? Yeah, no, so it's supposed to be 16, not 15. You've got 15 numbers here. And the average is 23. Now, that is bigger than 300, but obviously you can redistribute these, so it doesn't have to be. Okay. Sure. Okay, but with log we have a 30, because either we have a 30 or we have a -30, right? You can't not have a 30 and not have a -30. With log we have a 30. I think this will help us. With log we have a 30. And let's say the 30 is here, because once again we can like rearrange the rows and columns. So we rearrange the rows so that the 30 is here. With log it's a column that makes 30. Right. Now, that 30 must have all ones. Right, and I should probably, like, do this kind of thing. In order to get 29... Oh, no, you can still get 29 here. Okay, but in order to get -30, you now have to do it... Or -29. Okay, you now have to do it as a column. That's sus. Okay. And obviously one of them has to exist, right? At least. But isn't it the case that every time you add one of these things, the possibilities for the row sums just keep shrinking? Like let's say you have a -30. Now the -30 we already know, right? The -30 can't go here. It can't be a row sum, so it has to be a column sum. All right. Now, if that's true, then you get all minus ones. Okay. Now, what can the row sums be? They have to be between 28 and negative 28, right? Surely there's some kind of recursive argument to be said about this. Like, I wonder, do you even need this condition? Like, if you could have each number appear any number of times that you wanted, is that possible? Because it seems very dodgy. Like very, very dodgy. But it could be possible, actually. Yeah, I don't know. Maybe you have some kind of like staircase pattern. I don't know, right? But in this case, you do also have a bunch of zeros, and that is also very concerning. All right, so since the range is now 28 to minus 28. Interesting. All right. The argument is a bit annoying because you are allowed to skip one number, right? You are allowed to skip one number. But I think this still works. What you do is, let's say you don't skip minus 30, right? So log we have 30, and then let's say we don't skip minus 30. So we know we have a minus 30, and we know it has to be a column that sums to minus 30. What sums to 29 and minus 29? Obviously not a row, right? And then we know, of course, that at least one of them has to be summed to. Let's say it's 29. I'm going to delete this. I don't think that argument works. Let's say it's 29, and we're just going to put it next to 30 because we can. Right. And once again, we can rearrange the columns, so we can just log, okay, it's all ones, and then the last one is a 0. Because that's the only way to make 29, right? Okay, at this point, you've restricted the range even more. So now for these numbers here, they have to be between 28 and like negative 27, which is like very restrictive, I think. Oh no, it's negative 26. Every time you had a 1 there. Yeah. So these are now between 28 and minus 26. All the way down to here. It's a minus 28 to minus 26. And then the last one, that can be a 27 to a minus 27. Right. Okay. But it still means that nothing can make minus 29. And in fact, nothing can make minus 28. So now you use the argument with minus 28 and minus 29. At least one of those has to show up. And it has to show up as a column. Let's skip one for the sake of the argument. I want to see what happens when you skip one. So let's put the minus 28 here. Okay. Now we can't quite log stuff anymore because where you put the zeros is very important. In fact, you don't even have to put zeros, right? You can put minus ones and a single 1. So what are we going to do? Right, but I think the point of this whole thing is that like every time you put something over here, it like restricts everything. It restricts all the row sums. And then you get like another column for free, essentially, or something like this. Another column sum for free. Yeah, okay. I think what's going to happen is like every time you add a number to a row, like let's say we decide on this column and like we decide that in this, like, there's going to be a 1 here. So you look at this row. The before and after the range before is going to be 2 more than the range after. So before it was 28 to minus 26. Now it's going to be 28 to minus 24. Okay. So the before and after, the range will decrease by 2. Now I wonder if you can use that to your advantage somehow. Okay. Yeah. The problem is I don't think this argument works forever, and the reason for that is that every time you introduce some like zeros, right? Like the ranges kind of like they diverge from each other. Even if the range keeps getting smaller and smaller by 2 every time you insert a number, the intervals will diverge from each other. And that means that, like, slowly after a while, I don't think you'll be able to use this argument anymore. Okay. So one thing that I think is really restrictive, that I haven't really, like, we haven't really dived that much into this, is that there are supposed to be 300 zeros. That just isn't right, yeah? Like 300 zeros. If we go back to the 6x6 example. Also, sorry guys, I might be losing my voice a little bit, but I'm going to try and keep going. Going back to the 6x6 example, if we have 12 zeros, right? Let's just consider where the zeros can be. Yeah. Okay. So, let's put zeros in some random spots. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Actually, let's kind of put them here. Okay, 10, 11, 12. So, how many zeros do we have in each row and column? We've got 2, 2, 2, 3, 2, 1, and 2, 1, 5, 1, 2, 1. Now, these should both add up to 12. And they do. Okay, we're good. The problem is that based on the number of zeros, you now have a range for what the sum can be in that row or column. Okay, for example, if there are 5 zeros, your range is now limited to -1 to 1. Right. And this range, okay, I can see a method, and this could work. Okay, so for example, we know this range is going to be -5 to 5. Everywhere there's a 1, the range is -5 to 5. And everywhere there's a 2, the range is -4 to 4, of course. Everywhere there is a 3, the range is -3 to 3. Okay. Anyway, pretend we fill in all 12 row and columns, right? With this. Now this can only work if yes, okay. We need some kind of like I think it's called like majorization or something. We have like a sequence. 2 sequences that like add up to the same thing, but like one of them is like always higher than the other. If you take like the cumulative sum, like one of them is like always higher than the other, right? This is used in the statement of like Muirhead, right? I don't know anyone who like if you know Muirhead, right? You know this. But the reason we need this for this problem is that we know that, for example, we need, for the sake of this argument, let's just say we need all the numbers, right? From minus 6 to 6. We need a minus 6 and we need a 6. So this means we need two intervals that are going to be a minus 6 to 6. And then we need two intervals, from minus 5 to 5. We need two intervals, that's minus 4 to 4, and so on. Now, we don't necessarily need these exact intervals. So there are supposed to be 13 here, right? Okay, we know there's actually 12, but let's just say there's 13 so far. We don't need these exact intervals. These are just the most restrictive intervals. Which means if you don't have two 6s, you're screwed. If you don't have 4, 5 or more, you're screwed. If you don't have 6, 4 or more, you're screwed, right? So like, for example, this one, we can see that we don't even have any 6s at all, which means we're already screwed. And that's because every column and row has a 0 in it, meaning you can never achieve a minus 6 or a 6, right? Likewise, for the minus 5 and 5, we can see that we only have like, right, no, we definitely have enough. So we have 4 1s, okay, which means that we have enough of the minus 5 and aboves. Okay. Then, okay, we definitely have enough 4 and above, right? Because you would just need 6 of them, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have like way too many, right? You can kind of keep doing this. And maybe this doesn't work out in the end somehow. Okay. I feel like you probably can make this work somehow. So maybe this approach is not good, right? Well, here's another idea I just thought of as well, right? What actually is the sum of all the numbers from 1 to 30? Let's calculate. This is 31 times 30 over 2. Is this right? So wait, 1 plus 2 is 3, and that's 2 times 3 over 2. Yeah, okay, so yeah, this is the correct formula. I'm not off by 1. Okay, so this guy is, wait a minute. Oh, no, we're fine. Okay, so 31 times 15 would be 310 plus 155. So that brings us to 465. So this is 465. Okay. We know there's 300 of each number. And this 465 means that on average, if you add up all the positive row sums, for example, you would get like roughly half of this, right? And you have all the column row sums, you would get roughly half of this. Which means that it should be fine. I really feel like somehow like, yeah. It's the zeros that screw everything up, right? Surely. Okay. Let's. So we've tried analyzing the ones and the zeros. Surely it's got to be one of these, right? I don't know. The zeros just seem like really restrictive somehow. Let's try some more small cases actually. I wonder if we can get the 6x6 to actually work. Okay, so we'll log we have a 6, right? I have to make a decision now. We can skip -6 and just not have -6. Wait, we can't skip. Wait, what? Can we skip it? Because wait. The total sum of all the row sums and column sums has to be even. In fact, am I high? Doesn't the skipped number have to be 0? My god, wait. Cause, okay, whoa. Because we know, for example, that if you look at all the column sums, we know they have to add up to 0. And if you look at all the row sums, we know they have to add up to 0. Surely this means that you can only skip 0, right? Because you're like, okay, let's say you don't skip 0. What? Wait. Let me do a small case. Wait, what? Yeah, I don't know. Let's do a 2x2. What? So, but like a 2x2 is a bit trivial. So maybe do a 4x4. Let's say you have a -4, and you want to like. Wait, what? Well, -4 might be a bit trivial too. The 4 case, because you can't really do much, right? Like if you have, you can do like 2, 3, but then if you have like a 0. Okay, wait, like because essentially the point is that like you've got your set minus n up to n, and you want to partition it into 2 sets of size n, each of which sum to 0. The question is, can you do that if the missing number is like something other than 0? What? So let's say you skip 0. You go -6, -5, -4, -3, -2, -1. You've got a 0, right? And let's say you skip 2. So you've got a 1, 2. Oh no, sorry, we just skipped 2, 3, 4, 5, and 6. See the problem now. Oh, of course, bro. I'm so dumb, bro. What am I doing? Okay, so the sum of all of these numbers is not even 0. So if your 2 subsets sum to 0, then you take the union and they have to sum to 0. But this doesn't sum to 0. Oh my god. So the number you skip has to be 0. Oh my lord. That's so dumb. Oh my lord. Okay. Okay. So, how did it take me this long to get this? Oh my god, that's okay. Okay. Skip number has to be 0. Zero. Great. Okay, wait. This tells us a lot of information, actually, because now we don't have these pesky cases. So maybe the first idea does work now. Right? Remember, the first idea is like, okay, we can do it on this example here. So we've got all ones somewhere, and it's going to have 6. Now, that means we have to have a minus 6, because we know we skipped 0. And that means we have to have all minus 1s, okay? And now we have to have a 5 and a minus 5. But none of the rows can be 5 or minus 5, so that we can just put the minus 5 and 5 here. Now, we can log that this row is like this, but we cannot log the next column. Sorry, I'm not row, it's column. We cannot log the next column, because the 0 could be here, or it could be somewhere else. But we can fill in these minus 1s, I guess, right? And then the 0 could, like, you could either have this, or you could have like this. Okay. For the sake of diversity, I'm gonna make the 0 here. Right. Now you still can't have a 4 or a minus 4 in a row, so the 4 and the minus 4 have to go here. Now, this is very bad, because as we know now, right, there are too many 1s, and that is a contradiction. I don't think this exactly works quite the same when you use 30 instead of 6, but let's try it and see what we get. So we are back to a 30 by 30. We know that we have to have all 1s somewhere, and we get a 30. We then also know I have to have all minus 1s, and we also get a minus 30. Okay, so we also, no, it's the same. Okay, same issue. So we get a minus 29 and a 29, right? We know that. And once again, we can kind of do this to it. And with the minus 29, of course, we can do this. Right. This gives us a minus 28 and a 28. Okay. Now there are 2 ways to do a minus 28. Yeah, you can have like 2 zeros, or you can have a minus 1. I really think you want to have 2 zeros, because like you want to use as few 1s as possible, right? Yeah, okay. But the range of like most of these is now very small. It's like 26 to minus 26. And the range of this one is you've got a 1 right now, so it's minus 25 to 27. The range of this one is minus 27 to 25. Okay. Right. Now the trouble with this, of course, is that now... Oh, wait, no, we haven't filled in the 28s yet. Never mind. Yeah, okay. Yeah, the thing is, like, when you fill in the 28, like, let's say you fill in the 1 there, right? And then you do this. Actually, I shouldn't do that. Okay. And when you fill in the minus 28, you do this. Wait a minute. Oh, no. We're fine. Yeah. Okay. then you don't need a 27 here anymore because you can have... Oh, wait, no, you can't. What am I talking about? You can't have the 0 here. Wait, no, this needs to be a 1. Yeah, to balance out the -1 here. So, okay. Oh, yeah, okay. But you can still have this. Yeah, this still sums to 28. That's the column. Now, this can sum to 27. So you can't continue this argument any more than this, right? Okay, but if it were to be 27, right, all of these would have to be 1. I don't think that, like, breaks anything immediately. Okay. This is actually challenging. Got a 1. Yeah, okay, well, 27 could be there. It kind of does, like, destroy the whole thing. So I don't think you can use this kind of argument. I mean, if you did, it would be extremely messy. And of course this could be... Oh, wait, yeah, if you just kind of, like, do this, you can even get a -27 here, right? Yeah, and then, like, these would also be all -1s. Yeah, I mean, there are a lot. Oh, wait a minute. Oh. Okay, so I'm thinking now, right? We had an argument before which was like, we want to count, so you can't have too many, like, big numbers as the column sums. Like, you can't have 13 all the way down to 16, for example, because if you had that, that would get you to, like, over 300 ones in the grid, right? But then we were like, this argument doesn't quite work because you don't have to have everything from 30 to 16, right? Like, the sum of all the numbers from 1 to 30 is 465. Which means that on average, you can spend about 230 in positive numbers, right? So the positive row sums can sum to roughly like 230. And the positive column sums can sum to roughly 230. Okay, and then I was like, so that argument doesn't work. But that's only true if every positive column and row has only zeros and ones, right? If it has -1s, then you need more ones to kind of offset those -1s. So I'm thinking that maybe you can use this. This kind of feels promising, actually. Yeah, because like you have 300 ones and 300 minus ones. Yeah, okay. So even if you have like, on average, you're gonna have like, I don't know, 233-ish ones. In other words, okay, you want the positive column sums to sum to like roughly 233. Same with the positive row sums. Obviously, they can be anywhere from 165 up to 300, but it obviously cannot be more than 300, right? And now I'm saying that I don't think it can even be 233, because some of those sums will have minus ones in them, right? That's guaranteed. Like even if you try and separate all the ones and minus ones, if all the blocks of ones and a block of minus ones, so that like the column sums don't kind of, you don't need to compensate for the columns, but now you need to compensate the rows, right? Okay, so how do you make this argument? Because I feel like somehow you've got to have like what's the most efficient setup, right? Like some kind of like staircase thing, maybe. Like something where it's like this, right? And because in this one, like you've got like some of these things going on. I don't know if that's like is enough though. Okay. Let's say some row sum is 20. Right. Now either this was made with okay, well, I'm going to make a table actually. Number of ones, number of zeros, and number of minus ones. So you could have had 20 ones, 10 zeros, and no minus ones, right? Or you could have had a single minus one, 21 ones, and 8 zeros. Or you could have 2, 22, and 6, or 3, 23, and 4, or 4, 24, and 2, or 5, 25, and 0. I think these are the only possibilities, right? Yes, they are. Okay, so for every number, like in this case we've got 20, right? The sum is 20. For every sum, you have to pick one of these options, and you have to pick all of them in such a way that like after you pick everything, the number of ones, zeros, and minus ones are equal, and equal to 300. Yeah, it's a different approach, by the way, than what I was trying to do before. But like, I don't know how to like. Before I was trying to catch like how many ones and minus ones were kind of like nullifying each other. Is that number more than 67? Because if it is, then we're done, right? But I don't know how to show that, like, what number, how to, like, figure out the number, the minimum number, I guess. I just realized that 300 wait, isn't 300 a triangular number? Because, okay, wait. Is this why they picked 300? Like, is this why they picked a 30 by 30? Because 300 is a triangular number, and in this kind of like configuration is what we mean. That would be diabolical, man. Because 300 is equal to 1 plus 2 plus dot 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 plus 25, right? No, it's 24. Okay, so let's say that, you know, all of these are ones up here, and all of these are minus ones down here. We've got, like, you know, a 1 and a 2 and a 3 and so on, and like, you know, this here is like 24 high. So what does this whole thing look like? Well, since this is 24, we know this part is 6, so there are 6 zeros. 1, 2, 3, 4, 5, 6. We also know there are 6 zeros on this side, and that means that there is going to be 18 rows in the middle where they kind of collide with each other. Okay, and the 18 is going to work like this, right? On the first of these, you're going to have 1 annihilation. On the second, you're going to have 2 annihilations, all up to the 9th, and then you're going to have 9 annihilations. But then you're going to have 9 annihilations and 9 annihilations and then 8 and then 7 and 6. So the total in this particular configuration, the minimum number of annihilations, well, it's the same number of annihilations per for the rows and for the columns, but it's going to be 1 plus 2 plus dot 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 plus 9 plus 9 plus dot 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 plus 2 plus 1, right? And we know this is 36 plus 36, and that is, oh my god. Wait, no, sorry, what? This is 45 plus 45. It's okay. We're good. This is 90, yeah, okay. And if it was 90, we would be done. If we could prove that, for example, if we could prove that the minimum was 90, we would be done. Okay. This technique seems promising, right? Okay. Oh no, wait, we need the total number of annihilations, right? And we want to show that the total number of annihilations plus for the rows and for the columns. I think you need that. And we want to show that it's like greater than 135, right? I think that's the number. Interesting. Okay, there's definitely some kind of double counting argument here, because combined with this idea, I think we're done. I think it's a matter of calculation now. So here's the thing, right? Like, if you look at like how to choose something that works for 20, you only have 6 options, right? Each of them have some annihilation number. Now, the annihilation number in this case is just gonna be equal to the number of minus ones, because the number of minus ones is always less than the number of ones. But if you want a smaller annihilation number, it comes at a cost of more zeros, right? So in other words, let A be the annihilation number. Now we of course know that like A is just equal to the number of minus ones for this case of 20. But we have, actually no, let's make this n. Yes, n. Okay, and this can be A, B, and C. We have an equation, I think, for this. The equation is 2n plus b equals 10, and we get 10 by from 30 minus 20. So in general we have like what? 2n plus b equals 30 minus k, where here k equals 20. And I think if we just sum over the k's and over the b's, we get a relationship for n, and it turns out n is like bigger than 180, and then, oh wait, no, it just needs to be bigger than 135. And then I think we're just done. Okay, so let's do this calculation. But first, I have to figure out that this is always the right equation, because in this case, n is just equal to the number of minus ones, but sometimes it could be equal to the number of ones, right? The thing is, I don't think it can be both. Oh, right, wait, no, of course, 2n plus b is always going to be equal to 30 minus k. I think you can just straight up prove this, right? Because whatever b is, right, like, let's say you have a row, and you want that row to sum to 20, and you know that it has 6 zeros, then you know that 2 minus 1s have to cancel with 2 1s. Yeah, right? So this is always true. Okay. So what this means, if you sum over this equation for all k, right? Oh, wait, hang on. Yeah, is it 30 minus k? Or is it minus 30 minus k? It can only ever be 1, right, I think. Because if k is positive, yeah. It can only ever be one of them. So it's 30 if k is positive, and it's minus 30 if k is negative, I think. But anyway, we can stop using 30 minus k. We can literally just use like 0, and then 2n plus b equals 1, and then 2n plus b equals 2, and so on, right? This goes all the way up to 29. And then it repeats from the other side, right? So then you get like 2n plus b equals 29, 2n plus b equals 28, and then you keep going down to like 2n plus b equals 0. Okay, now at this point, I think you just like sum everything up, and I think you should be good. But I just need to first double check that these are the right equations, right? So this is supposed to correspond to the case where k equals 30. Now, in this case, okay, yeah, well, there's restriction on b, right? Like b has to be 0 in this case, and n has to be 15. Oh no, wait, sorry, what? No, sorry. B and n are both 0, right? That's the restriction. Okay, yeah. Because n and b are both non-negative, always. And then on the other hand, when it equals minus 30, you have the same equation. Yeah, okay. This makes sense. On the other hand, if you're trying to make the number 1, let's just draw out another table, which will make sure this is correct. So k equals 1 in this case, right? And the table will look something like this. And have our minus 1s, our 0s, and our 1s. Okay. Sorry, we should swap that 1s and minus 1s. So be consistent. Alright, so of course one way you can do this is have 1, 1 and 29 zeros. Okay, then have 2 minus 1, 27. 3 minus 2, 25. And you keep doing this all the way down to, you can have 1, 0, and then you have like 15 and minus, oh sorry, not minus. These are never minus, what am I talking about? These go up to 14. Okay. In this case, yeah, no, yeah, we're good, right? Like the annihilation number is, yeah, because the number of ones, sorry, the number of zeros plus the minimum of the minus ones and ones, which actually is always going to be the minus ones. Okay. So the annihilation number is always the minimum of the two, but the minimum is always on one side. It's either going to be this side or this side. Okay, so yeah, these are the right equations. So you sum up all of these equations. And, okay, what do we know? We know that the sum of all the b's has to be 600, right? Because for each of these, they have to be 300. Well, like, you split them arbitrarily into two sets, and for each set, they have to be 300, right? So okay, yeah. So that means the sum of all the b's has to be 600. And how many equations are there in here? 60. 120n plus... Wait. Yeah, there are 60. Okay. Plus all the b's, which we know there's 600 of. Equals the sum of all of these numbers. Wait, that seems like a really large multiplier for n. Anyway, what is this sum, right? Well, it's like 1 plus ... up to 29. That should be 29 times 30 over 2. But then you don't do the over 2 because there's twice. So it's just 29 times 30. And what is that? That's 9. That's like 900. No, the same. Yeah, it's 870. Yeah. What does this tell us? It tells us like wait, what? Oh yeah, okay. Oh right, the total annihilation number is 120 times n. Okay, yeah. So this means that 120n equals 870 minus 600. So it equals 270. Oh my god. Wait, did we say we have to prove it's greater than 135 or greater than 270? Because suspiciously 270 is exactly twice of what I said before. Right, I thought we needed to prove it's greater than 135. Did I make a mistake somewhere? Which I mean, like, even if I did, I think it's still fine, right? But like, right. Okay, so the total annihilation number is 60n, right? Like, so the annihilation number for each equation is one of the single n's, and technically all the n's are different and all the b's are different, right? So this is a bit misleading. And the total annihilation number is just the sum of all the n's. Yeah. But in each equation here, right, we know that we have 2n, which means that the total sum, yeah, like I should really like make the n's distinct, right? I'm gonna put like N1, N2, N3, like B1, B2, B3, and so on. This is N30 and B30. 31 and 31, 32 and 32, all the way up to 60. Okay, so we know the sum of all the b's is 600, and we know that the sum of all the n's, right? This gives us 2 times n1 plus dot 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 plus up to n60, which we can just say capital N, right, big N. So we know that 2 times the sum of all the nullifications, the annihilation, sorry, the nullification, is 270, which means that n is 135. Now, n being 135 does not finish the problem, because 135 plus 465 is exactly 600, right? But it does mean that we are now in a very, very restrictive Okay, let me think about what this means. So, what does the problem say? Oh, it says, is it possible that the 60 rows and column sums are all different? Bruh. No way. So you're saying it could be possible. I forgot about that possibility. The possibility that it could be possible. Yikes. I don't do the calculation wrong, right? It is like plus 600, and it is 870, right? Like 29 times 30. Yeah. And you subtract it, and it gives you 270, which is exactly 135. That's like the worst possible outcome. But it does kind of imply that it like is possible. So now I'm confused. Is it possible or not? I mean, speaking of which, how do you get that number of annihilations? Oh wait, is there some like even odd argument going on? If it is, then maybe we can still do it. We can still show it's impossible. Right, because like essentially what's going on here is like okay, I wonder like maybe that's not true. Like, you know, because obviously if you add up all the positive numbers from 1 to 30, we know you get 465. Which means that the sum of all the positive sums has to be odd on one axis and even on the other axis. Yeah, the problem is that the annihilations can happen over the negative sums too. So, okay. What this means is that if you have right, like, because okay, like when you have an even wait, what? Oh, yeah, the parity does not influence the parity of the annihilations, right? Because, like, you know, you could have. Oh, yeah, of course it doesn't. We already know that. Yeah, yeah, because, like, if k equals 20, the annihilations can be odd or even. Okay, so that doesn't affect it. Yeah, wait, maybe it is possible. It's possible for a 6x6. Alright, well, if I can construct one for a 6x6, I will be convinced that it's possible. Oh, wait, let me also repeat this calculation for a 6x6 to make sure it's not just a fluke. So the, like, annihilations calculation. So, what do we get for that one? 2n1 plus b1 is equal to 0. 2n2 plus b2 is equal to 1 up to 6. And then it goes back down to 0. Sum all of these. 2 big N plus, okay, so what is it this time? It's not 300 anymore. It's 12. Yeah. Oh, it's 24. It's 24 because it's counted twice. Equals 1 plus up to 6, which is 21. So this is 42. Okay, so now we've got n equals 7. Now, meanwhile, the sum of all the positive numbers, 1 plus 0 is okay. Sum of 1 plus 2 plus 6 is 21. And in this case, we have 465 plus 135 is 300. Sorry, it's 600, which is bad. And that's because 600 is what? Twice of 300. Wait, but that means in this case, it should be 24. But in this case, 21 plus 7 is bigger. No, wait, sorry, wait, what? It's not 7, I'm high. It's 9. Okay, but it's still bigger than 24. What the heck? Wait, the minimum number of annihilations is 9? Is that true? Like, I'm just gonna fill this in, right? Yeah, okay, so we've got all our ones over here, and we've got all our minus ones over here, as expected. And we can just do this, I guess, and we can also do this. Oh, wait. Oh, yeah, wait. I already know for, like, n equals 6 it's not possible. So wait, like, what? N equals 30 is, like, the first one, which it is possible? That would be crazy. Wait a minute. Surely the number of annihilations is bigger than 135. Like, this is just the ideal scenario, right? Like, solving all of these equations just gives us the ideal scenario. But I feel like if you just look at the original, grid, which is up here, the number of annihilations is like massive. Like just by looking at the rows, it's already like almost 90. Like 3 per row, and there's 30 rows of this stuff, right? If you were to add another 1 and another -1 to each row, right? That's already like almost 120, right? Like surely they just have to be more than 135 annihilations in total. Okay, I think I am convinced about that. Now the question is how to prove that. Wait, maybe the reason I got the number of annihilations is 135 is literally because solving this system of equations does not give us any new information. Because isn't that like we already knew this had to be the case? Maybe that's why I got that it's 135 there. If it was, then that was a massive waste of time. But surely, like, it just looks like it really has to be more. And like, and when I did this triangle thing, right, it came up to like what 180. So, what's the way to like make the ones and the -1s like interact the least amount of times? It's actually kind of an interesting question. I don't know, maybe you could do something like this, where it like only interacts here or something. 300. Okay. I mean, obviously the problem with that is like now the row sums and column sums are not correct. So maybe we should go with this strategy. But it seems like to prove it in this strategy, like there are so many cases, and I really don't want to bash this, Okay. I think what we've proven, though, is that if the column sum has a 30, then it has a -30. Then it has to have 29 and -29. And I think at this point, we've also proven that it has to have a 28 and a -28. So already having these three numbers already gets us to like a massive annihilation number. Right? Like here it's already like what? 86? Yeah, 86. Which is pretty close to 135. Okay. if we just have a few more numbers, I think we can do it, right? Like, okay. Yeah, like even by putting the 27 and the minus 27 here, you get tons of annihilation in this block, which we didn't have before. Yeah. Like surely this is how this problem dies finally. But I feel somehow like this is not the intended solution. It's just not that satisfying, you know, like this problem seems like okay. Anyway, hmm. Okay, wait. So we know that, for example, if we have a 30 and a minus 30, that generates 30 plus 30 annihilation. Right, we have 29 and a minus 29, that's plus 28 annihilation. 28 and a 28, that's plus 26 annihilation. Oh, in this case, it's actually plus 28, but yeah, in general, you can have plus 26 annihilation. Wait, that's a lot. Surely this works. Because, yeah, like, if you have, what? Oh, yeah, okay. You've got to, like, pair them up, I think. And we already know that we can pair up the 30 and the minus 30, the 29 and the minus 29, and the 28 and the minus 28. So, okay. 30 paired up with the minus 30, that gives us annihilation number plus 30. Right, by pairing up the 29 with the minus 29, we get annihilation number at least plus 28. 28 will always pair up with minus 28, giving us annihilation number plus 26. Now, okay, we can't do this any further. If you have both 27 and minus 27 in the rows or columns, then you can add 24. If they're different, though, then you can't. Okay, but surely there's like, you know, I don't know, like 27, you can definitely pair it with some like big negative number, right? Oh, yeah, wait. So like, consider 27. If you can't pair it up with minus 27, that means it's minus 27 must be on the opposite like axis. Let's say you also can't pair it with minus 26. That means minus 26 must be on the opposite axis. Okay. Well, I mean, like, you can have like, you know, all the remaining positive ones on like one side and all the remaining negative ones on the other side. But obviously, like, both of them need to sum to 0, right? So like, there has to be some balance. Nah, I feel like, like, I think I'm like, okay, approaching a solution here, but I really don't feel like this is the intended solution. It feels like I, like, overcomplicated it by a lot. Anyway, we've got this path, and we're almost finished walking it, so let's finish. Right. Okay, so we've got 27. Wait, no, like, let's say 27 is here. Okay, well, here we go. 26 and 25 and 24 and so on. Clearly you can't have too many of these. If you can just pair up some more of these, we'd be done. But I'm not sure that you can prove that you always can. Or like how to prove that you always can. 27 to 24, for example. Or like if you add 27 to 24 here. Even if you had like minus 23, you could still pair it with minus 23. You get something like 2 plus 20, which is still pretty good. Okay, I think we need to somehow use the fact that like the row sum to 0. It's not clear how exactly you can use that though. I think I definitely overcomplicated this. Like, this problem should not be this hard. And like the way I'm solving it right now, it seems like it's harder than what a problem 3 should be. Yeah, so like, why did they use 30? That is a question too. So, I just realized that, like, okay, if you have a log 27 here, and a log you have a minus 27 here, that reduces all of these, because now there are lots of ones which are going to be minus 1. In fact, almost all of them will be. Yeah. And the -1 means that the 26 reduces to 24. Aha. That means that 26 cannot be on this side anymore. That means 26 has to be on the bottom. Okay. So essentially, either 27 pairs up with -27, or it pairs up with, or -27 pairs up with. Right. 27 either pairs up. Well, -27 either pairs up with 27, or it pairs up with 26, because then 26 has to be at the bottom. Right. And in fact, 25. Oh. No. 25 could be here. Okay. Well, let's just put in the -26. Wait, if it works one way, doesn't it work the other way too? So here we've really shown that, like, 26 can be paired with -27, but doesn't that also mean that? Oh no, this is if it's not paired. Okay, if -27 is not paired with 27, then it's paired with 26. But this gives you a plus like 23. And we need to get this to 235. So what is it now? Currently it's 120 minus 247, 13. Okay, we're at 107, and we need this to be 135. Oh my lord. Okay. So it's either this, or you can get 27 with -27. So it's one of these two. Alright, that would give you a plus 24. But that's just better, right? But like maybe it like branches off at this point. Okay. So if 27 pairs with -27, let's say they're both here, right? If 27 pairs with -27, um, 26 could still go here. Okay, but I think you can make the same argument, like if -26. Oh wait, sorry, this is 26. Okay, yes, 26 could go here. But if -26 goes here, that reduces a lot of these down to 24. Oh yeah, but there's still like one that's like 25, so you can still get a 25 over here using that one. If like, wait, what? Yeah, if this is like a 0 and a 0 and the rest are -1s, you can still get a -26 here. But that leaves like two of them can still be. Oh wait, what? Oh no, it can't. Oh wait, what the heck? Wait, did I what did I do here? Isn't this supposed to be 24 already? No. Yeah, like what? Oh my god. 24 minus 24. And wait, are these supposed to be different too? Because they had a what did they have? If you delete these, right? This is what they looked like. This was like the best case scenario. And even then, there was still. Right, these cancel out, and you've got a 3 here. Oh, right, you know, you can get to 27 using this. So I think those are still fine. It's just that this goes from 24 to -24. Which means that you can't actually have 26 or 25. Wow. Wow, that's pretty good, actually. Okay. So if we have 27 and -27 here, then there's nothing to be -26 or -25. So they all have to be column sums. so that's the case here, right? If we can match up 27 with minus 27, that gives us plus 24. And then, yeah, tons of these. Okay, so we get, yeah, 26 and 26, minus 26, 25 with minus 25. I think that pushes you over the edge, right? So this gives you plus 22, this gives you plus 20, and yeah, that's way more than 135. Okay, so now the question is, what happens if you can't match up the 27s? So that's case A, right? Like, what happens if 27 yeah, if the 27s cannot be matched up. So we proved before that if, for example, a row is 27 and a column is minus 27, sorry, yeah, column is minus 27, and there's nothing to be 26 anymore. So the minus 27 matches up with the 26. That gives you a plus 23. So there has to be a 26 here. Okay. Okay, where does minus 26 go? It could go here, but then you get 27 and minus 26 pairing up, which is bad. But if it goes at the bottom, I mean, it would go over here. Okay. Okay, but you could have still 25 down here. Then what about 24? Like, you could still have something up here, which is like 24, I think. Now this is kind of annoying. Yeah, this problem surely does not finish like this. I mean, if you don't want matches, you know, you're the other 20. Oh, wait, where does minus 25 go? Wait a minute. I forgot about minus 25. Well, none of these can be minus 25, so minus 25 actually has to go down here. Okay. Okay, but like, couldn't you still have, oh wait, no, wait, couldn't you still have minus 24 down here too? Yikes, I don't like this. does this method actually just not work? That would be very sad. I mean, like, can't say I'm surprised about that, but yeah. But like, at least I'm pretty sure now that like the answer is no, right? It's not possible, because if it was possible, these column sums are like horrendous, right? Like you'd expect that if the answer is yes, there'd be some like nice pattern to the sums, but there isn't. So like, surely the answer is no, right? I guess okay, something that could work is, instead of trying to like force this using the grid, we could just force this like by using the fact that each set sums to 0. Alright. So how that would work is, if we know that there are 24 numbers left in here, I'm going to use a different color now. And these 24 numbers have to sum to 0. And we want there to be yeah, okay. Well, I mean, like, these 24 numbers could be like the numbers 1 to 12 and like -1 to -12. But oh right, that would leave the other numbers over here, and then you could pair those up, and then you would definitely just win. Okay. So the thing is, like, you want, like, you want 27 and -27 to be on different axes, 26 and -26 to be on different axes, and like also like 27 and -26 to be on different axes as well. So essentially you want like all the big positive numbers to be on one axis and all the big negative numbers to be on the other axis. But I don't think you can actually do this enough, right? But like, how do you quantify enough? That's the annoying part. So, okay, well, let's say that out of the 24 numbers, you pick some numbers like 27, 26, 25, 24. Okay, and then I mean, like, the other axis is going to have like the negative of these values, right? But like, this axis still has to have some negative values because they have to sum up to 0. So right, like, it definitely has to have at least at this point it has to have like -1 up to like minus, what is this? Okay, like this sums to 102. So I think it has to go to like, I don't know, minus 12, 13. It has to go to at least, like, I guess it has to go to like at least -14, right? And then the other side, you'd have like, okay, -27, -26, -25, -24. And you'd have the same thing. It'd have to go from 1 up to 14. But I think this just works. And if you don't do this, like if you, I don't know, just swap some numbers, it just makes it worse, right? Surely. Like if you swap the 24 with... that's such a hand-wavy argument. But in this case, I mean, like, you compare the 27 with the minus 14, and that adds, like, 11 to the annihilation number, which is actually pretty good, honestly. Because what are we at right now? We're at 84. And our target is 135. So to reach our target, we need 51. Plus 51 annihilation number. Right? I think that should be pretty doable. Because, like, okay, if you have 27 in one column, and, you know, like, if 26 is in the other column, then, okay, then your annihilation number just easy goes up by a lot, right? But, like, if you also have 26, then I think already at this point, this is so annoying. I mean, this can't be the intended solution. Also, it's making it way harder than I think it's, like, actually intended to be. And also way messier too, which isn't great. Okay, so with a 27, you need at least -1 to -7. Which means you need at least a -7 in the same axis. I mean, but that just adds 4 to the annihilation number. It's, like, not great, right? Oh, wait. Maybe what you do... okay. Maybe you do cases, but, like, yeah. Because, okay, wait, for example, you know that 27 can pair up with -7. Oh, wait, but that only gives you 4. We need something that's bigger than 4, definitely. Let's say 27 and 26 are in the same one. I think that brings you from -1 up to... Now we're at, like, -10 or something, right? Because that adds up to 53. Yeah, that brings us to -10, okay. So we've got a -10 at least. And the same biggest number has to be a... Oh, wait, you can't really say that much about the second biggest number, can you? Oh, no, but if you pair these two up with the two biggest negative numbers, okay, then it should give you at least... What is, like, 7 plus 5? 12? That's still not a lot, honestly. That's kind of annoying. Maybe you just do cases here, right? Like, okay. Assume that 27 to 24 are in the same axis. That gets you from -1 up to 14. And then you pair these 4 up with the 4 biggest negative, well, like the 4 smallest negative numbers, technically. And I think that gives you like, you know, minus 11. Actually, maybe even 3 is enough at this point. But it would give you at least 30 plus 30. No, wait, that gives you actually way more than that. Wait. Oh, wait, no, it's 11, 9, 7, and 5, isn't it? Okay. So that would give you like plus 32 annihilation points, and if you double that, that's enough. Because we know that none of the other ones would exist otherwise. Yeah, but then if the other ones do exist, you need a different case. Oh my god, there are so many cases though. This can't be the way you finish this problem. This is so annoying. But this method always seems like, you know, it could work, and then there are just like way too many cases. Oh, I don't know. Maybe I'm just not doing the cases right. Oh god. Okay. Well. Um. Like the time it would take to write this out too. Like, oh my god. Like maybe you can like case match this, right? Like, okay, you assume you have the 4 largest. Okay, then you're done. We've already proven that. Oh no, we haven't proven that. Wait, that is annoying. What the heck? Because if this minus 27 is over here, somehow. I mean, but then you get like plus 24 annihilation point. But like still. And there must be like another way to do this, but like I don't know. I feel like I'm too like deep into this case bash to go hunting for the other method, like the intended solution. Should I? I know this, like, you know, because this is technically a finite case bash, and I know this can work. But the finite case bash right now is like massive. Oops. But I know it works in the end. I don't know it works in the end, but I'm like pretty confident it works in the end. But I can't find a way to like make the case bash like short, you know? Oops. Yeah. Because, you know, you would want to like pair up the largest negative numbers with the largest positive numbers on each axis. and then show that like generates like plus 51 annihilation. At least. Right. Yeah, I don't really see a way to like make this case bash nice, unfortunately. I'm very tempted to like go to problem 4 and then maybe come back to this later, honestly. Maybe like I'll get a fresh perspective on it. So let's just do problem 4 first, honestly. It's very annoying. Okay. Alright, let me twiddle with the stream a little bit. Okay, let's have a look at this problem. Alright, let n be a positive integer and let this be a sequence of positive integers, all with terms at most n, and our balance by choosing these integers. Oh wait, these are different integers, yeah, okay. She then extends this to an infinite sequence by defining the next, wait, what? Alright, for each n is greater than big N. Okay, show that there are either finitely many strictly positive terms or finitely many strictly negative terms in the infinite sequence. Oh, okay, wait, what? Interesting. What does this really say? It's saying that if there are finitely many negative terms, then there are infinitely many terms greater than 0. Right, I mean, I don't care about how many zeros there are. Could be finitely many, could be infinitely many. Okay, right, well, wait, one more. So the contrapositive would be, or like the negation of this statement would be like, show that there are, oh wait, no, it says show that there are either finitely many strictly positive terms or finitely many. So one of those two. Oh, so there cannot be both infinitely many positive and infinitely many negative. Right. Okay, that seems like a pretty interesting thing to prove. Okay, okay, so how is the sequence actually defined? Let me try to understand what's going on here. Oh, I see. Okay, this means like it's the sum of the previous kn terms, where kn is just any number at most n. Any number at most n. Alright. So let's say that n is I don't know, 5. Right, then Annabelle begins by choosing the integers. Okay, the first 5 integers. So let's say she picks. Alright, and like we want to try and like break this. So we want to try and set like make something that has both infinitely many positive and infinitely many negative. And then I can kind of already start to see what's going on here. Right. This seems like a very like visual or like intuitive algebra problem, so it should be fine. Okay, well, let's say she picks, I don't know, 1, 2, minus 3, 3, minus 2, I don't know. And then like each next term is just like the sum of the previous few terms, where few is like between 1 and 5, right? You cannot have, apparently, infinitely many negative or infinitely many positive terms, which is kind of interesting, huh? All right, well, I guess let's try to break that. Let's say the next, let's try and see if we can like alternate between positive and negative. I mean, I know you can't, but we want to see why you can't. So let's take the sum of the previous 2. You get 1. Sum of the previous 2, you get minus 1. We're gonna get a positive now. The sum of the previous 4, I think you get 1 again. Sum of the previous 4, you get minus 1. Okay. Now there's no way to get a positive term, but you can get a 0 term. 0 term doesn't really help, though. It just decreases, how far back you can go. Interesting. So the next term has to be negative. Okay, wait, so wait, apparently the sequence at some point, like unless you start with like all zeros or something, or like, you make your sequence eventually all zeros, I think at some point it just has to go, like, it just keeps going positive. Yeah. Or all negative. And then at that point, it would just like grow exponentially. Right? I mean, it doesn't have to grow exponentially. You could just keep choosing the previous term. But like, yeah. Interesting. Okay. That's actually a pretty cool problem. I like this so far. So we can't make a positive term here. So let's make a negative term. In fact, I guess we can just make a negative. Oh, and it becomes even harder to make a positive term. Huh. Right, like at this point, like, I mean, well, like the next one is just gonna be like, okay. At this point, we've died, right? It's just gonna go negative. Very interesting. Now, of course, the reason it goes all negative is because kind of like if you take the cumulative sum, right, it will go like minus 1, 0, minus 1, 0, minus 2. And all of these are obviously negative. So whatever you pick, essentially, it's just, actually, I feel like cumulative sums might be kind of useful. Because, for example, right, before you pick this minus 1, the cumulative sums are 1, 0, 1, minus 1, and 2. Now you can pick one of these 5 numbers. Right, in this case we picked 1. Oh no, sorry, we picked minus 1. We picked minus 1. And as soon as we picked minus 1, now the cumulative sums are, you just take these cumulative sums and you subtract 1 from everything. So it was minus 2, 0, minus 1, 0, and then you just like kind of put this down here, so it becomes minus 1. And now you can pick one of these numbers. And apparently this process also ends up with all negative or all positive. Or like all, all non-negative or all non-positive, eventually. And at that point you lose, right? Apparently. Okay, interesting. I wonder if it matters that it's integers. Surely it doesn't, right? Like, the fact that the sequence has to be of integers, I don't think that actually matters. In some sense, when you pick the minus 1 here, this minus 1 can be ignored because you already decreased this. By picking a minus 1 again, you would just be decreasing it further. If you want to survive, you should try and like balance the decreases and the increases. And like you're already in a very precarious position here because like, you're almost out of negative numbers. If you want to be negative, if you want to make this more negative, you actually have to pick minus 1. Whereas if you pick a 1, then everything just becomes positive, and you go positive, right? This is very interesting. Okay. Let's try another small case. Right, let's actually just try the same starting sequence, but this time let's record the cumulative sums. So in this case we've got minus 2, 1, minus 2, 0, 1. Oh, yeah, that's not great in terms of choice, right? You can only pick 1 or minus 2 or 0. Yeah, but I feel like picking 0 is never good because it essentially just reduces your choice for the next term over, right? So we pick minus 2 before. Oh no, we picked 1 before. But if you pick minus 2, you lose immediately. Okay, wait. Let me figure out like why picking 1 eventually made it lose. Okay, so this is you get this. Now you don't want to pick 1 again. Whoops. So that's why we picked minus 1, because we kind of have to. Okay. We pick minus 1, this was minus 1, 0, minus 2, 1, minus 2. Okay. Right, and now you only have one positive number left, so you have to pick that one. What happened here? 1. You have to pick this one. Okay. And then there's only one negative number now. Wow. That's so interesting. So this is kind of the trajectory of the above approach. Okay, and then you lose. Right, somehow I feel like there's something to do with, like, oh, if you look at, you know, each column or something, you can probably deduce some interesting things. Wait a minute. Is it true that the range of choices always decreases every time you make a move? I think it does. I think it does. And the reason for that is because, well, okay, the range of this is 3, right? When you pick the 1, well, it's still 3. But since you've added the same number to all of these, then the range of these 4 numbers is still going to be the same. You've just added in a 1. Now the 1, if you have both negative and positive numbers, then the number you pick, wow, okay. The number you pick cannot increase the range if you have both negative and positive numbers. Oh wait, it can't increase the range even if you only have all negative or positive, right? Surely. Because like, yeah, even if you have all positive, 1, 2, 3, 4, 5, say, and then you picked, I don't know. Oh, no. Oh, wait, what? Yeah, no, you can increase it if it's all positive. Like, you pick the 5, and then you make a new one, which is 5, 7, 8, 9, 10, right? Now the range is 5, whereas before it was 4, right? But when you have only positive and negative numbers, when you have both positive and negative numbers, one has to lie, well, the number you pick should lie between the maximum and the minimum of these 4 numbers. Is that true? Surely it must be true. I'll prove that later, right? Because I think what happens after you prove that is, since the range always decreases at some point. Wait, does it strictly decrease? I don't think it strictly decreases, right? Because yeah, no. The range here is 3, and it's 3 after. The main problem is that when you, because the, like, you know, kind of, the window of numbers that you can pick from keeps moving to the right. I think the range eventually has to decrease. And I think these are the 2 parts that you need to prove this, right? You need to prove that well, okay, you need to prove that the range always eventually decreases. And obviously, if it always eventually decreases, it's going to be 0 at some point. And then at that point, at least at that point, but probably before that, right, you lose. Okay, so why does the range decrease? We know, well, I mean, okay, we don't know it can't increase, but I think proving it can't increase is probably quite easy. Let me fill in the range for all of these, actually. The range for this guy here is also 3. The range for this guy is actually also 3. Okay, now the range is 2, so it decreased here. Why did it decrease there? I think it's because we lost... If you look at this number here, it was involved in the range calculation always, up until then, right? Because, like, you see, like, 1 is the max. Oh, right, of course. Oh, wow. Yeah, if the number is the max, it's going to stay the max, right? Unless all the numbers go positive or negative, right? Like, but it's going to stay the max otherwise. You look at this 3, it's the max in these 5. The 2 is the max in these 5. The 1 is the max in these 5. The 2 is the max in these 5. and then it gets lost, which is why the range decreases. Wow. Very interesting. It's kind of interesting to note that no matter what you pick, it's because the range of these four is 2. And the range can't increase from this to this because it includes 0. The range includes 0. Yes. Okay. So this is 2, therefore this is 2. Right, but why is this 2? Well, it's because this is 2. Oh, and that's because this is 2. Huh. Okay. Right, but like, I'm not sure that matters actually, because I think what happens really is that since 3 is the maximum, when you lose the 3, well, like, you know, when you lose this column, it always decreases. Well, to prove that, you need to prove that none of these can surpass the maximum. Oh, and it obviously can't surpass the maximum because when you're picking it, right? Like, okay, wait. From this step, right? Well, like, just start from this step. You picked a 1. And so this number here is a 1, but this number increased to a 2. So it's still the maximum. Right. And when you pick a -1 next, this number is a -1, and this number decreases to a 1. And of course, this number is always going to be smaller than this number. Okay, I think I see where this is going. Also, I think I've pretty much solved this problem. Why does this problem seem so much easier than problem 3, right? See what I mean? Like this problem 3 must be, I must just be missing something. Because, like, combi is also supposed to be, I'm supposed to be, like, a combi main, right? But, like, the combi literally took me the most time, which is terrible. Alright, well, I mean, in this case, you know, yeah. So okay, the steps of this proof are, look at the cumulative, the range of the cumulative sum, which the cumulative sum is like, you know, the stuff that you can actually pick from, right, to be the next number. The range of that always decreases, and the reason why is because the maximum number and the minimum number can never be transferred, right? The titles of, for any given, like, big N numbers, in this case 5 numbers, right? The titles of biggest number and smallest number can never be transferred to a new number. And indeed, it can't even be shared, right? Unless that biggest number or smallest number is 0. Then it can be shared. but if the biggest number is 0 or the smallest number is 0, then we lose. Okay, so any new number that you pick, the maximum will still be the maximum, and the minimum will still be the minimum. In fact, it can't even be maximum equal or minimum equal, precisely because the maximum is not 0 and the minimum is not 0. And what this means is that after n turns, you're going to lose the maximum, right? After at most n terms, you're going to lose the maximum. And you're not going to be able to replace it. And that means you are going to, the range is going to decrease. And by infinite descent, it's eventually going to be 0. If you haven't lost by then, you will lose when you get to 0. All right, and I think that proves it. Right, I barely did any working for this problem. I love how that turned out. Okay, well, I guess we have to go back to problem 3, right? Okay, maybe I should like write down like the steps. Right, okay, so look at cumulative. Take its range. Okay. Equals max minus min, of course. Title of. Alright, well, I can say like next term can never be new max. Or new min. It can't even be equal max or equal min unless max or min equals 0. But in that case, we have already lost. After at most n turns. Okay, wait, then we're gonna lose. We'll lose the max, and min implies range will decrease. Okay, and then infinite descent. And then we're done, essentially. That's the proof outline, right? Okay, well, let's go back to problem 3. Problem 3. I think I'm going to try and look for the nice solution because even if you can do, the kind of annihilation solution by a massive case bash, I think it's kind of like a really unsatisfying way to end this Livesolve. So I'm gonna do it. I'm gonna try and find the intended solution, or just even a nice solution. Okay. So we deduced that the skipped number must be 0. How do we do that again? Well, the sum of the, okay, if you look at all the row sums and the column sums, their sums must both be 0. And so, yeah, if you take the union of them, the sum must be 0. And the only way for that to happen by missing one number is if you just remove 0 from the set minus 30 to 30. Okay, so yep, we know that the skipped number must be 0. That's pretty cool. I'm not sure that actually helps though. um, yeah. What are some other approaches to this problem? Can you somehow prove that like some number will always repeat, or like I swear I'm gonna face palm when I like find the solution to this problem. The intended solution. I still feel like the annihilation thing seems promising, but like I've already tried to get that to work a lot. If we remove the condition that it has to appear exactly 300 times each, then is it possible? I feel like it's more likely to be possible. Which means, well, I mean, you know, they clearly want us to use that somehow. I mean, I've already used it by saying that the skipped number has to be 0. Yeah, I don't know, like, you look at the like placement of the ones or the zeros. Right, I mean, the whole like annihilation technique is kind of like looking at the placement of both the ones and the minus ones together. Yeah, and seeing if that implies you have to have more than 300 ones in order to do it. I mean, at the same time, I still feel like having 300 zeros is really bad. It's like way too many. Like I feel like you could maybe do it if there were fewer zeros. Yeah, but like, how do you use that? Okay, well, let's try that idea again, right? Like, okay. We have 300 zeros. Now, on average, that means that we have 10 zeros per column and 10 zeros per row. Now, having a number of zeros, yeah, okay, like restricts what we can have, obviously, on that row or column by kind of bringing in the range, the possible range from both ends, right? Like if you have 1 0 in a row, then that row can only sum to like 21, minus 29 to 29. Yeah, the problem is if you have on average 10 zeros per column, then yeah, it's like totally possible for this to satisfy the that like majorizing thing that I was talking about earlier. Whoops. All right, so you know, and I feel like if you do this with ones, you also bring in the range, but it's just you know, you increase the lower bound by 2 every time. Yeah, so like I'm not sure that looking at the ones by themselves will help much. The other thing is, I feel like if this is possible, there should be like some like geometry diagram you can draw, where like, you know, one region is just ones and like another region is just zeros, and like the like, you know, area of each is 1/3 of the whole square, right? But I can't see anything that like would kind of resemble that, which you can do. Mm. And if you look at like, you know, the extremes, right? Like 30 and minus 30, then like they give you quite a lot of information, but like I don't think you can go that far with them. We already tried that quite a lot, right? And like I don't know, if you go to the other extreme, you look at like 1 and minus 1. I don't think that tells you anything, right? Somehow I feel like this annihilation idea is still the most promising idea. Hmm. Bruh. Okay. Maybe I just have to find a better way to count the annihilations. Um, uh, so the number of annihilations is supposed to be equal to exactly 135, right? I think that's what this proves down here. And like actually I could have figured that out without using this method on the right over here. Yeah, okay. I think whatever you do, the number of annihilations is going to be always greater than 135. But I don't know how to prove that without a massive case bash. Okay. The thing with like, you know, let's say if a row actually wait, what? Okay, wait. If you consider like 1, right? Now 1 can have up to 14 annihilations of ones and minus ones. But it can also have as few as 0, right? Like if you just have 1, 1 and like 29 zeros. Problem is, that uses up a lot of zeros, so you can't do that very much. So I just wonder that, like, okay, if you take into account all the zeros that you can actually use, wait, but don't we just get like the same thing we did on the right here? Like I thought this was supposed to work, but it doesn't. Like, okay, like if you say for 1, you know, we can draw a table with like how many ones and minus ones we use. Ones, zeros, and minus ones, right? Now you could use a 1 and like 29 zeros. And for 2, you could use 2 ones and 28 zeros and so on. But pretty quickly you'll use up all of the zeros, and then after that, you pretty much just have to rely on annihilations, and then I think that just gives you too many, right? Yeah, but then like, you know, you could sacrifice you could save 2 zeros, like you could have 27 zeros, but that means you need 1 extra annihilation. Wait, what the heck? That's supposed to be a 1. Yeah. Right, I think if you do this though, like you will just get like, oh, we have 135 annihilations, which is like not useful at all. Because that's exactly what you're supposed to get, right? Wait, why does this not work for 6 though? I remember when I calculated it for 6, it did not work. Why? Did I make like an arithmetic error somewhere? Let me just double check everything, right? Okay. Okay, so we know that the number of ones that can contribute to both sides is 600 in total. Both axes is 600. And we know that the sum of all the positive numbers is 1 plus 2 plus all the way up to 30. Right, now that's 465. Let me double check this calculation. This should just be 15 times 31. Yeah, that's 465. Okay, 465. Hang on, okay, so I'm gonna make a table for this. N is 30. Now, when n is 30, total ones is 600. And sum of positive numbers from 0 to 1 to 30 is 465. Okay, so this is 465. What was the calculation here? Oh yeah, we calculated the number of annihilations. Okay. How did we calculate the number of annihilations? Right. Min annihilation equals, so supposedly it's 135, right? Now, when n is equal to 6, the total number of ones that both axes see are, so it's what, like n squared times 2/3. It's 24. Okay, so sum of the positive numbers is 21 from 1 to 6, right? And the minimum number of annihilations, okay, so you have like, you want to make the sum yeah, wait, I mean, I know we calculated it was 9, but like it's 9 because in this case we get 2n plus 24 equals 42. 42 is twice of 21, and 24 is 2/3. Ah, I see. Okay. Wait, doesn't that mean we like made a mistake in our calculations? Because if it's like double 21 minus 24 to get, and you half that to get 9, right? we do the same thing here. Double 465. You get like 8. Wait, what the heck? You get 930. Wait, is that the... Wait, you've got to be kidding me. Is that the mistake? There's no way, right? Yeah, wait, what? That's not the mistake. The sum over here is definitely 870. So why is it suddenly... oh... Okay, no. It's because in this case, it goes up to 5. I see. So this one has a mistake. Right, so it's not 42 here. It's actually 30. Oh, yeah, okay, and then you get n equals 6. Sorry, n equals 3. And if n equals 3, then yeah, everything works out. Okay, so this method cannot be used to prove what we want. Right, like it's always going to tell us, like, you know, like we can just do it in general, right? Like this is n. Total number of ones is going to be 2 over 3 n squared. Sum of positives is going to be n times n minus 1. No. N times n plus 1 over 2. And the annihilation, minimum annihilation, according to this method, oh no, wait, no, never mind. It is supposed to be n times n minus 1 over 2. Yep. Okay. So then you would get, yeah, twice of this minus this, and divided by 2. Okay, now twice of that is 930. Wait, what? But then you get something that's bigger than 135, but you're not supposed to. Wait, I thought you were not supposed to. Yeah, it's because it's not that. It is, yeah, okay. Okay, wait, so what is this supposed to be? So like, n times n minus 1 minus 2 over 3 n squared over 2. Yeah, okay, and then what? Like you're supposed to add this up. Okay. Like, doesn't this just give you like something? Yeah, I mean, it's not supposed to work anyway, so. I mean, sum of positives is not what we want, right? It's like sum of, oops. Yeah, okay, it's not this one. Okay, so this method doesn't seem to work either. Well, I mean, it just gives us something that like we could have figured out much faster anyway, right? But then I wonder why they used 30. Maybe it's just a multiple of 10 that's divisible by 3. Bro, I swear this has taken me like over 2 hours now. Like I solved like all the other problems in like 30 minutes each or something crazy. And this problem is like 2 hours, bro. Or more than that, maybe now. I have no idea. Why is this problem so hard? What the heck? Why am I not getting this problem? Okay. Is there a 3 by 3 that works if you don't need the same number of ones, zeros and minus ones? The problem is that you need a. Oh wait, but then the missing number doesn't have to be 0 anymore. So, because I think if you have -1, -1, you just die, right? But like, if you have -1, -1, 0, that's 3 and a -2. Okay, so you can't have a -3, obviously. Well, you still want to have a 2, so I think this one has to be that. And then what, can you just like this? Oh, no, we get 2 zeros. This? Nah, that doesn't work either. Maybe the 2 has to be like this or something. No, but then there's a 2. 2? No, I don't think this works, right? Like you can't do it even if the number of ones and zeros is different. Oh my god. Okay. Damn, I am also really losing my voice now. Okay, so yeah, what is up with this problem? I still feel like trying to prove that the number of annihilations is greater than 135 has to be the way to go. So maybe there's like a way to do it that, where you don't need a case bash. Okay. Once again, we can look at this idea of, we know that we can force 30, 29, 28, minus 28, minus 28, and minus 30 to be on the same axis. Now, that would give us 84 annihilation. And we need to get to 135. So that means we need to get 51 more. And I'm just wondering, out of the remaining numbers, right? Like from 27 to minus 27, if you need to split it into two sets, each of which sums to 0, and if you just pair up wait a minute. Can we like combine these ideas somehow? Maybe that's a bit difficult actually. Okay, anyway, if they have to be split into two sets which sum to 0, right, and you like pair the largest positive ones with the most positive ones with the most negative ones, right? Like that kind of thing will generate more annihilation, right? Is it just always true that you will get at least 51 annihilation by doing that, right? And now the fact that they sum to 0 is important, because if they don't, then you can just put all the positives in one set and all the negatives in the other set, right? Okay, so now you've got like 27. Like 27 has to go in some set, but then like, yeah, the negatives, yeah. So here's the question, right? Okay, so if we look at all the numbers from... Oh, where's a good place to do this? Actually, there's like not much more space, so maybe we just go to the right a bit. You look at all the numbers from 27 to, well, they should be minus 27 to 27. We know that all the negative numbers will sum to 14 times minus 27. Wait, what is that? $378, I think. Okay. And the positive ones will sum to 378. Right. So we can ask for each set, what is it summing to? Surely this works. So obviously the positives have to be split and the negatives have to be split over the sets. So that means there will be a set which will have at least like 190. Wait, no. 189 on the positive side and on the negative side. Right. Yeah, because like you want to pair the most positive numbers with the most negative numbers. Okay. But you don't know what they are. And I don't think this one set alone is enough. Okay, wait, so to get to 189, right, what do you actually need? So you can go all the way up to okay, so what we need n times n plus 1 over 2 is greater than or equal to 189. So n times n plus 1 is greater than or equal to 378. So that means n is greater than or equal to something. 20. Wait, what? Wait. What did I do wrong? I'm so confused. What the heck? So the sum of the first n numbers should be bigger than 189. But this is just n times n plus 1 over 2, right? Wait, no, it's right. Okay, wait. So we've got okay, we have to figure out what actually it results in this. Okay, so n times n plus 1. Okay, so 20 obviously is greater, so it's like about 19 times 20. Oh yeah, no, it must be 19, right? Okay. And I think the fact that all right, this says that the largest number must be 19 or more, because if there's no 19, if every number is smaller than 19, you can't even get to 189, right? So there has to be a 19 on this side, has to be a minus 19 on this side at least, right? But like combining these only gives you an annihilation of 8, which is not 8, right? Which is not great. So like, okay, you can try to take the two biggest numbers. Yeah, but like even if you do that, I think you like in the end you only get like 8 plus 6 plus 4 plus 2, which is 20. And even if you double that, it still doesn't get you to 51, which is what we need. Yeah. The problem is like, what? Hmm. Okay. We got these numbers. Now, if all of the negatives and all of the positives were in their own set, then you just couldn't pair anything up. But obviously the sum has to be 0, so surely we can do something with that. Okay, wait, let's say we split the positives, because obviously the positives can't all be in one set, because then, you know, the negatives will also have to be all in that set. So we split the positives into 2 sets, and then we split the negatives into 2 sets. Okay. So like, okay. The thing is, like, if you put 27 in one set and 27 in the other set, 26 in the other set, then you know your annihilation is going to go up by quite a lot because some like one of like minus 27 has to be either in the set or in that set, and then you just pair them up, right? Maybe wait, I'll list the sets vertically actually. Okay, so then like, but like, yeah, the problem is like if you put 27 and 26, like what's the biggest positive number in the other set? On one hand, if it's big, right, that's kind of good. If it's like 20, then you know 27 minus 27 once again has to go in one of these sets, and same thing happens. But if it's too small, let's say it's like, I don't know, 5, that means you like know like a lot of numbers in the set. The set actually has everything up to like 6, right? Which also means that it has to have lots of big negative numbers, which is good. Okay, so somewhere between this, there's a balance. I mean, like, okay, you could have like a 25, and then like the next biggest. Yeah, but that's still, yeah. Um, okay. Wait. What if you just look at the sums, right? Like, you know, we have 2 lists of numbers. Maybe this one has 25 and 20 and I don't know, right? Like, and so on. And we look at the sums of these 2 sets, and then we get some, and some. And we know if we add them up, you're supposed to get 378, right? Now, the negative numbers also have to sum up to x and y, but the negative version of those. So they have to match. And depending on what x and y are, maybe there is a way to case bash where, like, I don't know, you take the numbers from like 20 up to 27, and these 8 numbers, depending on how many are in one set versus how many are in the other set, you just bash. Because like if all 8 are in one set, then you're done. And if it's like a 4-4 split, then you know you're done as well, right? Like, okay. Maybe this is the case bash, but we need to pick. Maybe it's not 8, maybe it's some other number. Before I think I was trying 4, but I think 4 is too little. I think it needs to be, maybe 8 is good. Alright, well, let's do 8. Well, 8 has 5 cases, right? 7 has 4 cases. wait, let me see if 7 cases can work. So like, if there's a clean way to do 7, so if you have 23, 22, and 21, and you match them with minus 27, minus 26, and minus 25. From this one you get plus 20, plus, yeah, no, this surely works, right? Like, plus 16. Yeah, that's more than 51, so I think 7 is enough. Okay. Take the top 7 numbers. So 21 up to 27. Now, split them into 2 sets, right? And depending on the number in one set versus the other, we should be able to reach some kind of conclusion. For example, if the split is all of them in one set, for example, so like 7 in A, 0 in B, then you know the sum of everything in A is like pretty big at this point, right? It's like 140. Oh, I don't know if that's big enough actually, but it's 168, right? At least 168. The thing is that in order to get to 168, the 7 most negative numbers have to sum to like something, right? Like okay, so it has to be okay, wait. Okay, so anyway, 168 is smaller than 1 plus 2 plus ... plus what? What's the smallest one that's greater than 168? So you double it and you get 336. And then you need n times n plus 1, 336. So 324 is like 18 squared. So it should be 18. So you go all the way up to 18. That's decent, I think. Actually, I think that just finishes, because the biggest 7 numbers have to sum to at least the biggest 7 numbers in here, which is 12 up to 18. So then you just match these up. So you've got like 12, 13, 14, 15, 16, 17, 18. And I know, like, okay, you know, it doesn't have to be exactly 12 to 18, but the fact that the top 7 numbers have to sum to greater than the sum of these 7 numbers means that when you match them up like this, the annihilation will be at least 15 plus 13 plus, so it's okay, the annihilation is way bigger than is it? Yeah, surely it is. 15, 13, 11, 9, 7, 5, 3. So 20, it's a 20, it's a 20, yeah, it's like 60 something. Yeah, so we're good in this case. So this case is done. Now let's say there's 6 in A and 1 in B. Okay, so there's 6 in A. We're just going to go with like the lowest possible bounds here. The 6 in A. So the smallest sum it can be is if you just simply subtract 27 from this. So you get 21 to 26. which we know is 141. 141 is less than or equal to 1 plus 2 plus dot 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 plus. Okay, so it's like what? 282. 256 16 squared. Should be 70 squared. Yeah. It's yeah, it should be plus up to 17. Okay, wait. This is a really weak bound though, because this is actually equal to like. Oh wait, what? 17 times 9. Oh wait, no, this is tight. Wait, isn't it? Isn't it 143? Oh no, it's 153. That's why. Yeah. That's pretty weak, which means that maybe like the either like our argument about like, oh, you match the top 6 with 21 up to 26. I'm not sure that works anymore. You need to be a bit more careful in this case, I think. But I think in any case, like I think you exceed it by quite a lot, right? Anyway, like because the 1 in B, even if you have 21 in B, it matches up with like 20 minus 27, which we're just gonna put as 27. Oh, actually, wait, no, maybe we shouldn't. Maybe I will put negative signs. So we've got the minus 27. I mean, do we know we have minus 27? Ah, right. Wait, whoa. We know minus 27 has to sharpen one of the two, and if it shows something this way, we can just swap it with the 17. Instead of pairing up 17 with 26, we just pair up the 27 with 26 instead. Oh, I don't know. Oh my god, are there more cases now? Oh my lord. Anyway, like the original argument was like, okay, you would pair the 21 up with the 27, and that would just already give you like plus 18 annihilation. And then you add on the stuff the extra stuff you get here, and it's like quite a lot. I think you end up with like 13 plus 11 plus stuff. But like, yeah, I'm not sure because like now this argument is a bit dodgy because this bound is quite weak. And then this might also not, like, you might not have minus 27 here, it might be in here, and now, oh my god. But, like, it surely works. It should be, like a decent amount greater than 51, I think. Oh, right, I think, okay. With the minus 27, I think you can assume that the minus 27 isn't here because, yeah, if the minus 27 isn't here, then the minus 26 isn't here. And you can match that up and match this the minus 27 up with, like, I don't know, like 26 is much better. And then you're like, oh, what if the minus 26 isn't here? Well, then you just match the minus 26 up with the 25, and then you match the minus 25 up with the new one. So every time you do this, like the annihilation increases by quite a lot. So like, yeah, the best scenario is where like minus 27 is in this set, and like, and then the worst stuff is in here. So you can assume minus 27 is in this set, I think. So that gives you plus 18 annihilation, which means we only need like plus 33 from this, which I think we can get pretty easily. But how do you prove this? Yeah, like if you have a bunch of numbers summing to 141, and you like match them up with 21 to 26. So like the top 6 numbers, what do they sum to, right? Like that's what we need. Kind of depends on how many numbers there are, but like, I mean, there's no maximum. It's kind of, yeah, it's a kind of like annoying calculation to do. I don't know. I trust that like when you do it, like it should just work. It should work. All right, yeah. Like wait, surely like even if you like delete the 17, it should work, right? Like even if it goes up to 16. Let's test this. Okay, so we've got. Wait. So 11, 12, 13, 14, 15, 16. We've got 21, 22, 23, 24, 25, and 26. Okay, so you've got a 12, 10, 8, 6, 4, 2. Yeah, that's way more than 51 now. Yeah. Like, even this just by itself is like 52. Okay, we're fine, right? We don't need this. Like, I think this method should just work eventually. Like, it's just a matter of like finding the right case bash, which is kind of sad that we didn't find the intended solution, but okay. 5 in A and we have 2 in B. In this case, you now subtract another 26 off from 141. So in this case, you get 115. I think. Ooh, that's kind of small. But in this case, you should just get like 1 plus 2 plus plus 230. So that means 18. What is that squared? Oh no, wait, what? 17. $15 is 225. Yeah, it's just 315. And that should give you. Wait, that's times A is 120, right? Okay, so even if you go from 14 down to like what 10. Now we're pairing it up with 21 up to 25. Okay, so you get like a 9, 7, 5, 3, 1. And on this side you get a 21 and 22, worst case scenario. Same reasoning as above. I think you can assume that you have minus 27 and minus 26 in here. Okay, and of course these are also negative. You have these, and then you've also got these, which amount to 18. And oh wait, I matched them up wrong, but I don't think it matters. Like this should have been like 26. So minus 26, and this one is minus 27. So in this case, you get a 19 and a 17. You sum all of these up, it's surely greater than 51. 20, 20, 12. Yeah, you're at like 61 now, right? So this one gives you plus 61 annihilation, which is good. Actually, I should be listing out how much annihilation they all give you. I think those going to give you like 70, right? Because this is like 10, 10, 20. Oh no, wait. It gives you 60, I think. 10, 10, 22. Yeah, this one gives you 60. So it's fine. And the first one is the sum of all of these things, which is 20, 20, 23. So it's plus 63. So this one is also fine. Okay. Finally, we've got 4 in A and 3 in B. Now for this one, I think you just do like 21, 22, 23. You match them up with minus 27, minus 26, and minus 25. All right. And then the other one, you've got 21, 22, 23, 24. I don't think do you even need this time? Because I'm not sure. I'm not convinced you do. Okay, so you match these up. You've got a 20, an 18, and a 16. Together that adds up to 54. So you're already good, right? Like you're already done. You're already done. But if you wanted to do the other side as well, wait, what is that? So that time we subtracted 26, this time we subtract 25, you get 90. Yeah, I think 90 is correct. Now we know 90 is, right, you add up to like 13 or something. Because 30 times 9, yeah. It's like 1 plus 2 plus dot 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 plus 13. That's 91. Okay, so now you can get like 4 numbers, right? So you just get 10, 11, 12, and 13. You match them up with 21, 22, 23, and 24. These are negative, remember. Okay. And that, of course, means alongside these, you also have 1, 3, 5, and 7, right? Yeah, cool. That's 16. This gives you plus 70 in total, I think. So this is fine as well. Oh, wait, no. It's a bit different because this does not need to be that. And minimum case scenario, you know. All right, these are not like tight as well because these are not tight, right? Okay, but it's like a lower bound. It's a lower bound. It's a good lower bound. Here's 9, 10, 11, 12, which means that it's like 0, 2, 4, 6, which means it's 66 instead of 70. Okay, but anyway, all of them are bigger than 51. So we're done. Wow, finally. Yeah, that took way too long. And also, I don't think it's the intended solution. I swear I'm going to like read the intended solution. I'm going to facepalm. Oh, my lord. Yeah. And, oh, actually, I think I should probably, fix this solution because if you add everything up to 18, what you actually get is 9 times 19, which is 171. So that means that these should actually be minus 11 to minus 17. Minus 11, minus 12 to minus 17. And so what you actually get is not 15 down to 3, but it's 14 down to 2. Right. Yeah, that's 17. So this is 2, 4, up to 14. So instead of 63, you would get 56, which is still bigger than 51, so it's still safe. Okay, and yeah, the reason that you can do this supposedly is because the largest 7 numbers will add up to at least what these add up to, right? And the reason that's true is because right. Okay, so here's the thing. If there are 18 numbers, then obviously you're going to have 12 to 18. If there are 17 numbers, you can take this kind of averaging thing, right? Oh wait, no. I mean, okay. Well, surely, okay. If there are 17 numbers, then obviously you have to have at least 11 up to 17. Right. But more generally, the argument that you make here is you take every number 17 times, and then wait. I just need to convince myself as well about this argument. If you have 17 numbers, you list them all out. You've got your A1, A2, all the way up to A17. I think, wait, you list all of them out 7 times each. So it's A1, A2, up to A17. And you list them out 7 times. And then you take these sums. So you take the diagonal sums, right? And there are 17 of them. And the average is 7 times the average of the sum of these, which we know is at least 168. Right. And we also know that these are the top 7, and they're also the max out of all of them. Wait a minute. Yeah, okay. But the thing is, this one has some wraparounds, right? It's this kind of thing, which maybe you need to use. Yeah, you definitely need to use the fact that they're distinct to be able to get this fact, I think. But if you are able to get their sum, you can just take the sum of these and the sum of these, and then add them up, all of them, and then subtract 30 for each pair there is, and then the result will be what you're supposed to get. So then the individual numbers don't matter, it just matters what their total sum is. Right, and I just want to show that the sum of the largest 7 numbers is at least at least this much. The sum of these 7 numbers. No, I think it's easy, right? Because, okay, you look at you look at the bottom number. If the bottom number is too low, and also the sum is still the same, that means maybe you move the highest number higher and the bottom number lower, right? Well, since these are the top 7, every other number has to be smaller than these, which means that you now have one less number to work with. So, before this you could have 10 numbers over here, but now if you move this down to -10 instead of -7, you only have 9 numbers here to work with. So that means you can't even get it to add up to 168, right? So yeah. If you have 7 numbers, their sum has to be at least the sum of these 7 numbers. Okay, and that proves it, I think. So we're like completely done. I'm convinced it's watertight. Like maybe I should write it up at some point, but like that'll depend if I have time, which I don't know if I have. We'll see. Oh my god. Okay. Well, honestly, I think I'm gonna try to like, yeah, I'll search up these problems and I'll kind of give them a review. My voice is really dying now. I apologize for that. Wait, where will the discussion be on EOPS? What, like, because they don't even have forums for BMO2s. Surely it will be on Discord. UKMT general chat. But I don't know, like, maybe I can try ALPS BMO2 2026 problem 3. Wait, let me just go on ALPS first. High school Olympiads. I search, right? Maybe I can just enter the text, yeah? So, surely if I just search like 300 times, it'll come up, if it exists. Okay, maybe it's not on AOPS then. €60 and column sums. Oh, there we go. Here it is. Okay, let's see what they did. I initially expected this to be case measurable. Have row with 31s and row with 30 minus 1s. Actually, this seemed like time fallacious approach here is a bit smarter global approach. The sum of all 3 numbers is 0 and 69 is 0, namely this. Okay, so the missing sum must be 0. Yeah, okay. Consider the lines, rows, or columns with sums 30, 39, 28. It's S for sum. S. Sure. Each such line contains at least that many ones equal to its sum. Yes, that's true. So the total number of ones is at least this many. But yes, wait, what's S? Oh, yeah. But in counting this, some cell can be counted twice. Yes, that's true. The number of lines in the above counting is 31 minus S. Yeah, okay. And so if there are R rows and this many columns, then the number of... Oh, you're kidding me. Wow. You've got to be kidding me. Oh my lord. I am actually face palming, man. The number of lines is this. Okay, yeah. There are arrows and this many columns that intersect this many times. Okay, yeah. Individual inequality. Hence the overall amount of 1 is at least this. Try S equals 10. Oh my god, that's crazy. Yeah, okay. Damn, I didn't realize. Yeah, like if you like don't go all the way down to 1. Ah, yeah, I just didn't expect because I guess I didn't realize that you can count the number of intersections as well. Oh my god. Okay. Yeah. So I just kept thinking like, oh, the sum, no matter like where you go down to, it's always going to be less than 600, right? So that I use it. Ah, yeah, yeah, okay. Wait. So wait. Are they saying that like wait? So S equals 10. Oh yeah. So you go all the way down to 10. Oh right. And instead of every intersection, you only get 100. Oh wait, what? S equals 10. So you've got 21. You've got 21. Yeah, and like in a 10 by 10. Oh, wait. Even if this is 0, right? It doesn't go all the way up to 600. Because a lot of them are for like the negative ones. Oh, I didn't consider that as well. Yeah. Yeah. I'm just bad at combi, I guess. Sad times. Well, I mean, I guess it's cool that like I found an alternative solution, I guess, but like it's such a bad alternative solution that I'm like really not proud of it, to be honest. All right. Well, I'll also look at some of the other ones too. The problem is that it's kind of going to be annoying to search them up. Or will it be? Maybe it's going to be easy to search them up. Oh, why is it taking so long to search? Can you filter by tag? Is that a thing? No, right? No. Okay. Wait, can you not filter by source? Okay, let me search the text. Oh, and it was a geometry. It's gonna be hard. Maybe you search for up. I don't know. Search some text up. Huh. Maybe they only posted the third problem. Yeah. Well, I mean, I guess I'm not too bad. I mean, I'm glad that someone did so that I could like figure out what the solution actually is. Yeah, I don't know. How did I not get that? Yeah, I don't know. It's late, guys. It's late. I blame the lateness, bro. It's 5 a.m., bro. I really need to sleep. Also, my voice is dying. As you can hear, this is now an ASMR session. Okay, no. Okay, bye-bye, guys. I'm gonna go to sleep. Oh, wait. There's some, there are some more chat messages. Wait, someone said it was like D7, maybe D8 for problem 4. That's so. I swear it was like the other way around for me, right? Like, problem 3 was like D8. Well, like usually if you give me 2 hours or like 2.5 hours, I can solve like D9 or 10 combis. So I don't know what happened here. I definitely overlooked something, right? I mean, I overlooked the intended solution, which, you know, and conversely, I solved problem 4 in what, like 30 minutes or maybe less. Yeah. But to be fair, also problem 4 is the kind of problem that like I think it's like really suited to my like approach or like my solving style. So I guess that helps, right? But yeah, I thought it, if I were to like rate it like without context that it's like BMO2 problem 4, right? I would have rated it like maybe like D5. I don't know, right? But yeah, I guess we'll have to see the stats to know. Problem 3 is very similar to something rated D9 in POTD. Well, I like I it's the like problem that's like based off, right? That like a lot of people said like, oh, it's just copying, and I think the solution for that one is probably I say I don't know if the idea of looking at, because I feel like I got the idea. It's just that I got the main idea, but I didn't quite get like one of the bounds. I didn't consider like one of the bounds correctly, right? Although to be honest, I don't think that, yeah. So kind of just judging after having read that solution, I feel like it shouldn't be that hard. Like I can see why people put it as problem 3, but like yeah, we'll have to see the stats again, right? Like yeah, maybe even though the argument looks simple, it is actually really difficult to find. It's like really hard to judge difficulty in hindsight, right? Anyway, I definitely learned something today. Um, I guess I eventually managed to solve problem 3 as well. Well, technically, I think I solved it like quite a bit earlier because I knew it was a finite case bash at that point, right? Like I didn't want to go through with the whole case bash. So you nearly saw tuned in a couple of hours ago, and so you nearly saw me about not finding the last bound. Do you mean like the solution, like um, where you count like the number of intersections? Because I think the argument where you count the number of intersections is the hard part. Because like if you're just trying to like double count, like everyone knows you're supposed to double count somehow, right? Like you add up 1 to 30, and then like and then you for like, each one you can use 2 times, but then you get like 600 is greater than 465, which is definitely true, right? But yeah, I'm gonna end the stream. I think I'm gonna go to sleep. All right. Well, we'll see you in the next live solve. Hopefully that one goes better. Yeah, kind of ironic that I'm combi main, and it took me like 5 times longer to solve the combi problem than it did for me to solve each of the other 3 problems. Oh well, you know. Um, I guess that's just the nature of combi. All right. Well, we'll see you in the next one. But